Suresh. The session was really informative. And afternoon session was conducted by Dr. Ajay Bino, Dr. Achil Chandran, Dr. Franklin Brugare, and Dr. Gia Jose. So it's time to start today's, before that, we start today's exciting session, and we are grateful to present a token of love and gratitude to Dr. Gia Jose, who had taken yesterday's session. For giving the memento, I welcome Dr. Rani Alfonsa, the head of Chemistry Department. Thank you, ma'am. So it's time to start today's session, and the first plenary talk is going to be given by Dr. Reggie Philip. It's an honor to introduce Dr. Reggie Philip, a distinguished researcher and head of the Ultra-Fast and Nonlinear Optics Lab. Dr. Philip's groundbreaking work spans several cutting-edge areas of optics and photonics. Significant practical applications. His pioneering contributions continue to shape the field of ultra-fast and non-linear optics, making him a true leader in this domain. So please join me in welcoming Dr. Philip.
But do we talk about the frequency of light? Because anyway it has a frequency also, isn't it? So how do you calculate it? You know the velocity of light. So c by lambda will give you the frequency. If you make that simple calculation, you see that the frequencies are very high, like 10 to the power 14 hertz. So that's a range where the frequencies are. So the light, basically visual light, we will be mostly concentrating ourselves into the visible spectrum, concentrate only on the visible spectrum. So when you put a molecule or an atom in a light field like that, the field, and another thing, we are concentrating on only the electric field, not really on the magnetic field. Why? You are BSc students or MSc students? Mostly BSc students, right? Okay. So you must have seen the picture of electromagnetic radiation with electric field going like that and the magnetic field at 90 degrees to that, isn't it? Now remember one thing. The amplitudes of these fields are not the same. They are equal. Electric field this much, magnetic field the same, but they are not. The amplitude of the magnetic field you get by dividing the amplitude of the electric field by the velocity of light. And what is the velocity of light? It is a small number or a large number? It is a large number. So the large number comes in the denominator. So that means the magnetic field amplitude in electromagnetic radiation compared to the electric field amplitude is very, very small. So therefore, normally in worrying about the effects of the magnetic field when light matter interaction happens. So that's why we only talk about the electric field interactions. Okay. So now in that electric field, the electron will oscillate like that. At what frequency? 10 to the power of 14 hertz, right? So it is this oscillation which results in all kind of phenomena. The absorption is not going to be increased by 2 times. It's going to be more than that. Okay. That is why the exponential law. That's what the exponent actually means. So now, and we basically measure a quantity called absorbance. That is what we measure. If you normally do this, there are two options in a spectrophotometer. Either you measure the transmittance in percentage, or you measure the absorbance. So mostly people report it is a minus log of a number t. Does t have any unit? It's only a percentage, right? You can say t is 0.5, 0.7, maximum is 1. Which has no unit, you are taking the log of that, which is again a number. So it's only a number. There is no unit for absorbance. But many people don't know this. Anyway, that is all for linear optics. So whatever the linear harmonic oscillator, that behavior of the electron gives you normal results like dispersion, absorption. Imagine the light that you put in to your material system is much more intense than the normal light. This is normal light, right? We have tube lights, we have LED lights these days, sunlight is there. But if you put a laser beam there, the laser beam is much more stronger, much stronger than the normal light. And you have done this simple pendulum experiment, right? For +2, I'm sure you have done that experiment, many of you. So if you look into the textbook, you will see there is usually here, there is a sentence which says, make sure that your oscillations are small. So in MSc Physics, there is actually a chapter in classical mechanics called add more terms into the expression for the displacement. So these are called higher terms. The moment you add these higher terms, so this will be like an x squared term will be there, an x cubed term will be there. Actually it runs into infinity. But then beyond x square and x cube, the effect of those. So therefore, we usually confine ourselves with the second, that's x square term and the x cube term. There's no need to go really beyond that unless you are going to apply really powerful laser beams. And that kind of laser beams, if you apply to these materials, the first thing what happens is the material gets damaged. So you have no material to study anymore. So therefore, you limit yourself to these principles. We modify the Hooke's law to include the higher terms. And once you do that, now you can immediately calculate a potential. Because the potential in which all this happens is F is equal to dot dr. That is from it's a normal equation to calculate the potential. So when you do that, you can see that you have those terms, half m omega naught square x squared plus there's an x cubed term, then there is an x to the power 4. So now what you see here is that in x, there are even order terms and also odd order. Either it is x squared, x to the power 4, x, all that are positive quantities, right? When you square a number, you never get a negative number, right? It's always positive. But x cube can be negative. X to the power 5 can be negative. So you just take the first two terms. X squared term, it's a parabola. You take only the x squared term, it's y is equal to ax squared. That's the equation for what? There are no math students here, right? So, but physics students are supposed to answer. Y is equal to ax squared is a parabola, right? Yes. Look at that first term. Is that? So you see the parabola there. But now you add the second term to that. You have an x cubed term. Okay? So there is no parabola now. It gets modified to another shape like that. So the result of this is that you have the nonlinear polarization, that you have chi2 e squared plus chi3 e cubed. Now what is a polarization? Don't get confused with the light polarization, which is the orientation of the electric field in electromagnetic radiation. This is about the electric dipole moment of the material. Now you apply the electromagnetic field, the electric field causes polarization, dipole moment, electric dipole, right? So you have additional terms in that. So these additional terms in the polarization will result in nonlinear optical phenomena. Frequency is not altered in linear optics. Frequency is not altered. Color may get altered, but frequency is never altered. That is not so in the case of nonlinear optics. Two beams of light have no effect on each other in linear optics. Right? Two waves will pass through, right? Think about a pond, you put two small stones there, two different places. Waves will start going. Now what happens where waves meet each other? If you carefully look, you will see that they just pass. They don't interact with each other. They just pass. That is not the case here. They will interact in optics and create some frequencies, different frequencies. So we have a lot of differences like that. Some phenomena which and their applications. Second harmonic generation. So this is like getting twice the frequency of what you put in. For example, a very good example, I'll show you that a little later. Color gets completely changed. You can change an infrared beam to visible beam. You can change a visible beam to ultraviolet beam. It is possible using some crystals. Four-wave mixing, that's another, where waves get mixed up and they give new waves, new frequencies, waves. That is interesting. Because of self-phase modulation, actually two things can happen. One is the refractive index gets modified. The other is that a laser beam can focus all by itself. How do you focus a beam normally? You need a lens, right? Without any lens, you just put a material there, the right material, beam will start focusing. You don't need any curvature or anything. The beam has to be a Gaussian beam, that's a condition. Then nonlinear absorption, nonlinear refraction, we actually work in that, mostly in that area. Stimulated Raman scattering. So you know about Raman scattering, right? Since I am from the Raman Institute, I should tell you a little bit about Raman scattering. I won't go into much detail. But normal Raman scattering is very, very weak. It's very difficult to record that. In his original recordings, Raman took a lot of time to record Raman scattering in photographic plates in those days. Nowadays we have much better systems. Regular Raman scattering can be recorded very easily these days. But there is something called stimulated Raman scattering. In this case, the Raman light, or what we call the Stokes beam, comes out like another laser beam. You need a laser for this. Use laser. Now you generate, like for example, take acetone. Acetone is a normal solvent. Focus green light into acetone using a lens. You will actually see red light coming out of it. It is like the input laser beam. All properties same as the laser beam. Power also, like you will get 10%, 20% conversion. This is called stimulated Raman scattering. Because acetone has a vibration at 1000 centimeters. That's something. So such phenomena happen in nonlinear optics. Then nonlinear optical microscopy is very important. You know, the ruby laser was the first laser to be invented, isn't it? By someone by the name Wayman. He got a Nobel Prize also for that. So people used that ruby laser which emitted in red, and they irradiated a quartz crystal with the red light coming from the ruby, and they got violet light. So that was the very first demonstration of second harmonic generation. But something very funny happened when this paper was printed. In those days, it was not like online publishing or anything. Everything used to be, in the press. So everything is done manually. You have to really put blocks for each letter and all that, and then print it. And then there used to be people who will look at the proofreaders. So the proofreader, this is the way it was reported. This was the original picture. But you see an arrow there. In the place of the arrow, there was no arrow to begin with. It was a very small spot. So that was the output of the spectrometer. And they were trying to show that if you excite at that wavelength, at the longer wavelength, you will get a very small light here. Now the guy who was looking into the paper, the proofreader knows no science. He found a blemish there. He thought it's a blemish. Somehow happened in the printing process. So he took an eraser, the white eraser, neatly erased that part out, and that is the way the paper came out. The key point in the paper was it had disappeared. So then people started asking, you are claiming that you have second harmonic, but where is it? We are unable to see anything. So finally the journal had to write another note saying that sorry for our mistake. This happened during printing. It was removed and then they published the original picture there. So such funny things have happened. But nowadays second harmonic generation is so common. We use it on a daily basis. We use KDP, KTP, BBO, that kind of crystals for converting mostly the 1064 nanometer infrared radiation from an ND laser to visible at 532 nanometers. So this is so common. And then nonlinear refraction to photon absorption. So this is optical curve effect. One manifestation of that is what I told you, self-focusing and variation in the refractive index. The refractive index gets modified in time. So you need to use a pulse laser for this. I'm not going into the details of that. Another interesting effect is two-photon absorption. What is two-photon absorption? So we have all studied in school that if there is an energy gap, okay. Absorption of light is basically the absorption of photons by a molecule or an atom. Now for this to happen, the energy gap should match the energy h nu of the incoming photon. If the energy gap does not match the photon energy, absorption will not happen. This is what we have studied in school. But then this is not completely true. So as people say, they teach you all lies in school. Why do they say that? We are taught classical mechanics, right? We are not taught quantum mechanics in school. So one can claim that we are not being taught the right science. So they are lying to us. Our teachers lied to us, even though they knew, because they are all, your teachers are master degrees at least and PhD degrees. So they know that they are lying to you. Okay, take it as a joke. I'm not very serious here. Classical mechanics is always an approximation of quantum mechanics. So it doesn't matter. Similar way, two-photon absorption is something that can happen. Here, the energy of your photon needs to be only half of the energy band gap. But if the intensity is high, that means you have to use a laser for this. What is intensity? Intensity is basically the number density of photons in a given area. So if that is high, then two photons can be absorbed together by a quantum mechanical process and it can go to the plasma. Now that kind of phenomena will happen in nonlinear optics. And there is something called excited state absorption, which will look very similar, but it's not exactly the same, because in two-photon absorption you have no real energy level in between the starting level and the terminal level. But in excited state absorption you have real energy states, real electronic energy states in between. So this is another area where people make mistakes. Many people will measure excited state absorption and then they will claim that it is two-photon absorption, which is technically very wrong. Alright, so now for the botany department, I will show some NLO measurements in pigments. We have actually done this. I'll show you a paper, some 2-3 papers we have published. So what are natural pigments? Pigments are colors, right? So you can get colors from various sources. So here, they are present in all living matter. They are there in animals, they are there in birds, for example, right? So even dogs, I think, I don't know whether the skin of dogs with different colors, there's a black and white dogs are there. I don't know whether that's a pigment, I don't know much about, but think about a butterfly arrow, that maybe there are pigments there. Now coming to plants, certainly there are pigments. So they can be found in leaves, flowers, fruits, vegetables, etc. So there are 3 main categories in plant pigments. They are chlorophylls, carotenoids and flavonoids. And this is where most of the naturally derived colors are there. And there are also synthetic pigments. We can make colors. Dyes can be synthesized in the lab according to our requirement. Actually, I used to know a professor. He is German, very old now. Once I was to his lab, and he is an expert in making dyes, and he has a business of making dyes. And these dyes are extremely expensive, and he is already a multi-millionaire. That's what I heard. So if you know how to make dyes properly, that's a good business you can do. Well, so this is chlorophyll. We know chlorophyll is the green pigment, has a lot of role in photosynthesis. This is the chlorophyll molecule. You can also see the absorption of chlorophyll B and chlorophyll A. So these are two slightly different molecules. Then there are carotenoids. They cause yellow, orange and red colors. So here you can see different types of carotenoids. The molecular shape of the molecule that is shown here. Then flavonoids, they produce red, yellow, blue and purple colors. Again, this is the absorption spectrum of those flavonoids. Now, I'll just tell you about one work that we did very recently, and it is just out. I mean, it's online now in the area of photochemistry and photobiology. So we took the teak leaves. So the leaves of teak are not really used much. The timber, of course, and we know what teak is used for. So the leaves are usually neglected. So my student actually took the teak leaf, and she suggested, she told me, sir, we'll try this, let us see what we get out of it. So then there is some processing. It's not difficult at all. I mean, you wash it first, because you have to remove all the soil, all the sand, everything. Wash it cleanly, then powder it, then there is something called solvent extraction. Put in some solvents like dimethyl sulfoxide, dimethyl formamide, even acetone, sometimes even water will do. So keep it like that for 24 hours or 48 hours. Then the dye will come out of it. There are dyes, right? Teak leaf has a color. You look at the teak leaf next time when you see a teak tree. The color will come out. So now you have to filter it. You have to centrifuge, filter, and do all those things. You will get a very clean liquid out of it. So that is the sample. That is the sample that, and I will keep it in the refrigerator because you may want to use it for a month or something for various measurements. First thing you do again is take an absorption spectrum, as you can see here, and from that you can understand what are the components in this dye. Remember one thing, we have to look through quite a bit of botany journals to understand what is there in teak leaf. As physicists, we are not really good at those things. But my student and I actually read through some botany journals, and we found that at least there are 50 compounds. That's a minimum number in teak leaf. It should be way more. So the absorption that you get is not really of any particular compound. It is a consolidated account of what is there. So, but then there are 2 or 3 components which are really prominent there, and the effects that we see, the nonlinear optical studies, are mostly based on the performance of those materials. So this is the fluorescence that is in there. Then FTIR spectrum you can take. You can alternatively take a Raman spectrum. So that will give you information about the vibrations in the molecule. So that tells you about the bonds. So this is the molecular signature, FTIR and Raman. The IR spectrum is the signature of the molecule. Using that you can find out what are the components there. So that is taken and analyzed. Now we did an experiment called the C-scan. So this is very popular. Very popular in nonlinear optics. So basically what we do here is, as I told you, the nonlinear optical phenomena, they're all dependent on the intensity. So at very low intensities, you are not going to see this. But as you increase the intensity, you will start seeing the phenomena. So your experiment should be devised in such a way that it should be possible for you to increase the light intensity and then decrease. You start from a very low intensity, increase to the maximum intensity you can go, and keep measuring something, whatever you want to measure from that. So this experiment is designed in such a way. So what you have here is you have a laser and the laser beam coming out. A key point here, a key component here is the lens. So you use the lens, you focus the light using that lens. Now you can see when a Gaussian beam, usually these are Gaussian beams. When you focus that, you have a focal region. And remember one thing, it is not like what you see in school textbooks. In school textbooks, in geometrical optics, you will see beam going like that, right? And then there is a point, and we say focal point. Now what is the size of the focal point? think about a point mathematically. Does it have any size? A point has no size, isn't it? Quite efficient. But that is not physically true. The Gaussian beam actually never, there are diffraction effects. So you cannot really focus a light beam below a certain number, a certain size. So it has that size. Typically, if you, for our laser beam, if you use a 10 centimeter lens, it will come down to something like 10 microns. So you cannot focus it any lower than that. So that 10 micron size is your focal point. Now the thing is, you can change the size of your beam from something like 3 or 4 millimeters to 10 microns just by focusing that. Now imagine you are putting your sample in that region and just moving your sample. Now just by moving your sample from a point near the lens to the focal point, you can very easily change the intensity of light seen by the sun. That is the basics of the C-scan experiment. And then just measure the transmission. So you can measure two things here. In one flavor of this experiment called the closed aperture thing, you can measure the nonlinear refractive index, and in the other one, which is called an open aperture experiment, you can measure the nonlinear absorption coefficient. So we have done both. That is what you see there, and our experiment is automated because moving the sample and taking reading, you can automate, like use a stepper motor for that, interface with a program. All that is done by ourselves. Program is written at home. Even the stepper motor, initially we were using our own, but of late we have bought stepper motors and drivers from Newport, which are, they have better resolution, even though that resolution is not really required for this experiment. So we have them now. And our own stepper motors also we have. So this is an experiment even colleges can think of doing because the cost is very less. You can set up this kind of an experiment using a low-cost laser. One can even use continuous wave lasers. You don't really always need to use pulse lasers to get results out of this. So in low budget, this can be done. So this is the result of continuous wave laser C-scan. We used very normal green NDR CW laser, which costs about 3 lakhs, I think. Relatively cheaper compared to the price of other lasers, of pulse lasers. Now this is what we get. We get both open aperture and closed aperture data. And from this, by fitting the data to theory, it is possible for us to get the values of nonlinear refractive index and nonlinear absorption coefficient, which we have done. And we also used a pulsed NDR laser. In both cases, the emission is in the green, 532 nanometers. That is what we use. And this is what we get here. Again, you apply the theory to, the solid lines are theoretical lines. The points are the experimental points. So one thing you can see, the theory doesn't exactly agree with the experiment, right? So that sometimes happens. You cannot expect the experimental measurement to exactly match the theory. There are different reasons for this. Sometimes we get very good agreement, sometimes the agreement is not that good. So if your sample is optically very good, optically clear, clean, then you can expect to get good agreement between theory and experiment. If the sample scatters and all that, then it will be a bit difficult. But still, you can make, you can calculate and you can get the numbers. So this is this paper, which is now online. We published this in Journal of Photochemistry and Photobiology. Couple of other samples also are now being studied, and we have got results, and we have communicated to. One paper has gone to optical materials. It is under review now. It is another very similar extracted dye from a natural product. All right. So now let us come to 2D materials. So what are two-dimensional materials? Very good example is graphene. Graphene was the very first 2D material which was publicized or discovered, as far as I know. So it has very broadband absorption at optical and terahertz frequencies because of its energy band gap is close to 0 for graphene. So therefore, it absorbs everywhere at all the frequencies, which is a good thing. In some cases, it's not so good, but there are applications. The zero band gap and effects such as polycloaking will provide unique functionalities for graphene-based photonic nano devices. So So that is the advantage of graphene in electronics. And it exhibits saturable absorption, which plays an important role in laser applications. And it has a very large nonlinear optical response and ultra-fast photo-excitation dynamics. That makes it an ideal test bed for studying and 2D physical systems. So this is a kind of a benchmark material based on which you can compare other materials. By the way, while I was coming to the college, I saw a workshop, and there they have written in the board graphene coating. I have no clue what they mean, because graphene by nature is a single layer, and there are few layer graphene, but how can you coat that in a car? And I don't know, I really don't know what they mean. Anyway, so it has also come down to the local workshops. So this is the energy level diagram. Description for various electronic processes in graphene. So like you can see, the photo excitation, there are A, B, C, D, there are 4 pictures there. Picture A shows the absorption, light absorption process. Then you have interband transitions, relaxation in B. Then relaxation you can see there, and then there is polyclop. Polyclop means when the upper states get filled, then absorption becomes difficult. There are states are filled, so because of quantum mechanical rules, then it is difficult to fill the upper state. That's what is meant by polyclop. And 2 photon absorption processes, second harmonic generation, third harmonic generation processes. So all that you can see there. Now there are also other materials. Graphene is not the only material. So we have transition metal chalcogenides, then black phosphorus, hexagonal boron nitride, perovskites, topological insulators, and all that. And there are also hybrid materials which contain 2D materials, such as composites with dyes, plasmonic particles. The metal nanoparticles are very plasmonic. 2D crystals, silicon integrated structures, and all that. So we have a lot of such things. Now, to select a few of these, their structure and spectral domain of applications are like this. So if you take HPN, you can see the energy band gap is very large.
and Dr. Reggie Philip. Now we may proceed to the next session. It is my honor to introduce Professor Raman Singh, a distinguished expert in the field of material science and engineering. Professor Singh's groundbreaking research focuses on the relationship between nano and microstructures and environment-assisted degradation of materials, as well as innovative nanotechnology solutions to mitigate such challenges. His extensive work includes advancement in the use of cutting-edge materials like graphene for corrosion resistance and the development of novel coatings and alloys for diverse applications, including aerospace, defense, and biomedical implants. Professor Singh's academic contributions are unparalleled, with over 265 peer-reviewed journal publications, 15 books and book chapters, 60 plus plenary lectures, and leadership in international conferences. He has earned global recognition. He holds prestigious guest professorships at ETH Zurich, serves as editor-in-chief for leading journals, and has guided 53 PhD scholars from diverse disciplines and cultural backgrounds. Today, Professor Singh will share insight into his groundbreaking success in developing CVD graphene coatings on mild steel, a truly disruptive approach that offers remarkable and durable corrosion resistance, setting a new benchmark in material engineering. Please join me in welcoming Professor Raman Singh to enlighten us with his exceptional work.
Raman Singh is my name. I come from Monash University, and I'm very, very happy and honored to be here at this conference. I like to come to Kerala. I like Kerala, and I also like Malus. I like the Malayali people. I like Kerala because it's beautiful. It has backwaters. In fact, I came last year with my wife and I went to Alipi and I had overnight boating and all that. She liked that and she's not happy today that I'm here alone. But she will be coming after some time. So that's about Kerala. I like Malayali as well. I've worked with quite a lot of them. I worked at Indira Gandhi Center for Atomic Research in Kalpakkam for about 8 years. And I think about 30% of the scientists and other employees there are Malus. So I know Malayali people quite a lot for two reasons. First, Kerala is amongst the most educated places on the entire planet, not only in India. That's one reason. But also I found generally, unless you are going to throw an egg on me today, I found Malayalis are very respectful people. They are very polite. I have never seen two Malayalis fighting. I mean, I haven't lived here enough, but they don't fight. They are very polite. But that's not the reason what I like them for? I like them because they are also very, very firm type of people. If somebody does anything wrong to them, they don't tolerate. They are respectful, they want people to be respectful to them. But if you don't do proper things, they will fight for their rights. So that's what I like Malayalis for. Is that correct? Yes. Good. And I also like them because the place where I come from is entirely opposite to that. I understand. Because you don't mind, I was speaking to them. Thank you. Yeah. All right, those who are online, you didn't miss much. I was talking about Kerala and Malayalis. So, no, that's fine. So that's what I'm here for, and I will come back here again. I was a bit worried that it is 3-hour drive from Cochin airport to this place, and I can't even pronounce the name of this place even now. So that's okay. But I like because Nelson gave me a very good, Nelson, your academic staff, he gave me a very good drive from Cochin to here, and you know, scenery around was so beautiful, nice, winding road and all that. I really liked it. I thank two people for being responsible for me being here. One perhaps you have not seen, you saw him only online yesterday. His name is Ajay Vinu. He's a very good friend of mine in Australia. We conducted a conference together where he was convener and I was in the committee. It was a very good conference where 2 Nobel laureates attended and I was responsible for organizing one of them. So it was a good conference and we have been knowing each other for some time. We are very good friends. He is much younger than me, much younger than me. And also difference is that I have hair on my head, he doesn't have. So I'm thankful to him because he was to come here and he called me one day. I'm in India for 3 months on Government of India's Spark Fellowship and I'm based in IIT Kharagpur primarily. So he called me, hey Raman, I think you are in India, can you do me a favor? I was supposed to go to a conference, I'm not going, can you go? And all that. These people are very good, they will look after you, you will feel very good. I said, don't tell me that. You want help, I will help, I will go there. But he was correct that these people are very nice. The second person is Dr. Arun Raj, who was instrumental in me coming here, and Prashant, who is also convening secretary. He gave me company over dinner last night, and of course Nelson, who gave me drive from Cochin airport to here. Hopefully he gives me drive back, unless I've given him enough problem. Anyway, I'm not here to talk about that, I'm here to talk about this particular topic. And I'm really thankful to Professor Philip for 2 reasons. For 3 reasons in fact. One, that he talked about what Raman spectroscopy is, and I will be using it. Nobody works on graphene without using Raman spectroscopy. When I give a talk to someone who is not from science area, they think that it is me who invented that. My name is Raman Singh. I said, no, his name was not. And so that's one thing. Second thing is that he also talked about graphene, so I don't have to go into the fundamentals of graphene. As a matter of fact, I'm not as capable as he is to talk about graphene, because his whole center talks about such materials, and he's a physicist. I'm always scared when I face a physicist. They can always ask you very difficult questions, and so before he asks you questions, I submit to him that I don't know as much as he does. Okay, so that's one. Third thing is, he said that on his way from Bangalore to this place, he was surprised how can one coat thin material, 2D material like graphene on metal. That's what this whole talk is about. So that part I can say that, okay, perhaps I know a little bit. Yeah. All right, so let's get into the talk. This title, how much time do I have? Because I understand you have someone lined up from Indonesia at 11:45. He can wait. All right, okay, you can tell him whatever you like. So, my talk is about developing chemical vapor deposition coating of graphene on steel. Okay? And I have used this word. If I knew that I had a very well accomplished physicist sitting in the crowd, I will not use this word, because when you say something like disruptive, people who are very fundamental scientists, they challenge you. How can you call it disruptive? So I didn't know that Professor Philip was coming, otherwise I would have removed that word. But it is for durable corrosion resistance. I hope that by the time I finish this talk, I would be bringing home the point that what was achieved was indeed disruptive. And I will tell you why it was disruptive in a second. So I come from Monash University. It is the largest university in Australia with about 85,000 students, and it is within the top 40 universities in the world. As a matter of fact, Monash is the youngest university to be in the top 40 in the world. Also, it is a member of GOA, Group of 8 universities in Australia, which are the most research active universities. I work in these two departments written there, and I published in this name. There are no two authors, the same person, because Indian names can be tongue twisting, very difficult for Indian names in general can be tongue twisting, but if you have Malayali or Andhrai name or Tamilian names, even worse. So they can't. So I have to make it simple because I have to live there, you know. So thank you very much for having me here. And when I give a talk, particularly to students, please feel free to raise your hand if you have a quick question. I don't mind being disrupted, even though I'm doing disruptive research. I don't mind being disrupted, okay? So you can ask if you have a quick question. I can manage my time. I can go at a pace where I can finish in time. So I have about 45 minutes, is that right? Yeah, okay, good. So first of all, why we are talking about corrosion? We are talking about corrosion because it is an expensive affair. An economy like United States loses about $300 billion every year because of corrosion. Every developing economy or developed economy uses about 3 to 4%, up to 4, even more than 4% of its GDP through corrosion. So it is an expensive affair. But this problem has been with us for a long time. Ever since we started to use metals, this problem has been there. Those who do chemistry or even physics would understand why I'm making that statement. You have minerals available to you for ages. Most minerals are iron oxide, aluminium oxide, zinc sulfide. What I mean by saying that is that these minerals have been with us for millions of years, and they have been thermodynamically stable. That's why they stayed like that. So iron oxide is far more stable thermodynamically compared to iron. But what we do, by extractive metallurgy, we change iron oxide to become iron so that we can make steel. But in that process, I have converted a very stable material chemically and thermodynamically into an unstable material, which will have tendency to go back to become iron oxide. That's nothing but corrosion. So we have inherent problem ever since we started to use metallic materials, that this problem of corrosion means that corrosion is an old phenomenon. And also it is an expensive phenomenon, as we just now saw. So people have done almost everything possible to solve it, like having corrosion resistant alloys, like stainless steels, aluminium alloys, or having coatings, the coatings that you have on your car or scooter or quite a lot of e-vehicles that we see in India. So people have developed quite a lot of coatings, different types of coatings. Also we do cathodic protection. I don't have time to go into details. But the point that I'm trying to bring home is that people have done almost everything to avoid the problem of corrosion because it is old phenomena and it is expensive phenomena, right? That's why doing anything disruptive or novel in this domain is very, very challenging, right? Because everybody has done. They have been much more smarter people than me. Earlier, they have done everything, right? So if you do anything, it is very challenging to do anything disruptive. But if you do, it is highly rewarding. You imagine a situation where you do not have to use stainless steel. A graphene coated mild steel will be working much better than stainless steel. That's why it's disruptive. Just to give you a bit of flavor of what we achieve, we had graphene coated nickel and we did corrosion tests. I know everybody is not from corrosion area, including Professor Philip. So what you do here is that you take a material, you expose it to electrolyte, which is conducting, and then you increase the potential in the anodic direction. Why anodic direction? Because corrosion is an anodic process. What is anodic process? It is when you take metal, it dissolves to become metal ion. In corrosion, that's what happens. So a material which is resistant to generating ions, you can say it is corrosion resistant, right? So what we do here is that we increase potential. By increasing potential in the anodic direction, we are trying to force the material to corrode. And that's where we compare the two materials, which one is more corrosion resistant, right? So here, that's what we are doing. That it is, we increase potential and we change current. Why current? Because if you have more ions, you have greater current. And here you can see that this bare nickel corrodes at much faster rate compared to graphene coated nickel. Okay? About 2 orders of magnitude because it's a log plot. So intercept of these two arms gives me corrosion resistance. Clear? And graphene coated nickel showed 2 orders of magnitude superior corrosion resistance as compared to, what is 2 orders of magnitude? More than 100 times superior, more than 2 orders of magnitude, as compared to bare nickel in sulfuric acid when you do this typical experiment which is called polarization experiment. This polarization is different to the one that Professor Philip was talking about. It's electrochemical polarization. Okay? But what I'm trying to show you through this slide is that intercept of these two arms is same irrespective of whether you are doing test in sulfuric acid, alkaline environment or neutral environment. So graphene coated nickel gives same corrosion resistance. It does not care about aggressiveness of the environment, whereas the bare one does. See that intercept is different in different conditions. I will talk about this a bit later. It is very, very corrosion resistant material we have generated. We take a proper nickel copper alloy and you develop graphene properly on that. You see, even if I am trying to force it to corrode, it's the same type of law, just axes have been reversed. See, here I am trying to force it to corrode by increasing anodic potential. It refuses to corrode. That current axis is the same. It does not. If I took bare nickel copper alloy, it will corrode like hell. You see how rapidly it corrodes, how rapidly the current increases. And then we did what is called electrochemical impedance spectroscopy. I won't go into details of that. What it does is that at the lowest frequency, the magnitude of impedance gives me corrosion resistance. This is one of the unique behavior because of what I showed you earlier, which normally people don't find. So graphene is giving very robust corrosion resistance. And here, seeing is believing. After this test, you do scanning electron microscopy, you see not much corrosion at all. But if you didn't use proper alloy, then the coating starts to get disrupted. This paper was published just last year in a very reputable journal, small. It is, I must say that publishing a paper in journal like small is far more challenging in corrosion domain because they will say, oh, it's old field and all that. Who wants to publish paper in dirty business like corrosion? So that's, in that sense, it is. If it was some nanomaterial energy or biomaterial, much easier. Corrosion is far more difficult. This is what I will be showing you again. This paper has just recently been published again too. very reputable journals, Small and Carbon, where we could successfully develop graphene on mild steel. It is difficult to develop graphene on mild steel, almost impossible it has been. And once we develop, you can see that graphene coated mild steel gives very good corrosion resistance, whereas 2 millimeter thick mild steel sample would have been finished in a couple of 100 hours in this aggressive sodium chloride environment. This work, as a matter of fact, also won an award in a competition in Boston a few years ago. So what is graphene? Professor Philip already talked about it. We know what is graphite. It is a layered structure, and one single layer is graphene. If you separate one single layer and you characterize it fully, and if you did it before 2010, you would have won Nobel Prize, because Nobel Prize was given for this. The 2 Nobel laureates, Osha and Gein. I have had meetings and dinners with both of them. In fact, one of them attended my talk on graphene. But anyway, so graphene has extraordinary properties: electrical, thermal, electron mobility properties, surface area, a couple of orders magnitude superior to any competing material. Graphene has much better electrical conductivity, a couple of more orders of magnitude superior compared to the best metal with best electrical conductivity. And people, just for your information, people are working on using graphene for electronic applications. Like when you have electronic devices like this laptop, quite a lot of energy is lost because of thermal effects. When I have a metallic interconnect, it has resistance, so you have thermal loss. And imagine how much of electronic devices we use, mobile phone, laptops and all that, so we lose quite a lot of energy because graphene has almost nil resistance. So if you make interconnects instead of metals using graphene, you will not lose thermal energy. And what Professor Philip showed you is that it has 0 band gap, right? So that's why it is very conducting. But by doping graphene, you can increase the band gap. You can use it as semiconductor. So on the same material, certain area you have doped, it is semiconductor, you can use it in place of silicon-based device, you can use as semiconductor, the rest of the area will be conductive. So it's a very, our university has a research center funded by government on that topic. Last 3 topic aspects, I'm not talking here, I will come talk about that in the subsequent slides. So graphene, as a matter of fact, is 100 times stronger than the strongest steel. But what is very unique about graphene is that it is strong, but also it is tough. Generally, strong materials, as you increase strength, toughness goes down. What is toughness? Toughness is brittleness. You take a plate, china clay plate, the teacup made of ceramic, you drop it on the floor, it will break because it does not have toughness. But you take steel, you drop it, does not break because the toughness, the energy, impact energy it took, it can absorb. Why I'm talking about it in the domain of graphene? I'm talking about it, graphene coating. I'm talking about it primarily or mainly because coatings have this problem of being brittle. If you take ceramic coatings, they break upon impact because they do not have toughness. Graphene has toughness. Second property is graphene is very inert. It does not react with hydrogen fluoride, highly aggressive chemical, let alone common chemicals like chlorides or benign acids. Even highly aggressive chemical like hydrogen fluoride does not attack graphene. Why I'm talking about that in the context of coating? Because quite a lot of polymeric coatings degrade because of chemical reaction, like polymeric coatings can be attacked by alkali, right? Polymeric coatings can be attacked by ultraviolet radiation. Graphene will not. Graphene is so stable chemical. And the third one is equally important, that is, graphene is impermeable. There is no such thing called everlasting coating. If you are talking about polymeric coating, every coating eventually fades. That's why your coatings on your car, in spite of car companies doing everything, it fails eventually because coatings have pinholes, defects. And through those defects, the corrosives can permeate through. Okay? In the case of graphene, ideal graphene, it will not happen because the little hole that you have in the middle of the hexagon is so tiny that even helium can't pass through. So the agencies that cause corrosion, like water, oxygen, chloride, they will not have any chance, but they are far, far larger than the hole that you have. So what I showed you is graphene is impermeable, it is strong and tough, and it is inert to aggressive chemicals. So, and there is no other material which has all these properties present in one material. So can graphene be an ideal corrosion resistant coating? So I think part of the query that Professor Philip had, I think I have answered, that it has properties to be. How do we develop graphene? His question was that how do you develop to the graphene coating on metals? And that's what I didn't know that he was coming, but I think I organized my talk to yes. So you develop graphene coating on metals by chemical vapor deposition. What is chemical vapor deposition? In chemical vapor deposition, you take a piece of the metal on which you can develop graphene, put it inside the furnace, heat it to about 1000 degrees Celsius, then you send hydrogen with the help of argon. Argon is a carrier gas and you are using hydrogen. Why? Because if you know aluminum diagram, most of the engineering material, engineering alloys, they will have a native oxide layer. It is humanly impossible to have oxide-free surface on copper, nickel, steel and all that. You have to go to the partial pressure of 10 to the power minus 23, 24, 30, which is humanly impossible, right? Just by having vacuum, you can't have oxygen-free environment. So you want to get rid of that. You want to get rid of that oxide layer. So you send hydrogen. Hydrogen reacts with copper oxide, it leaves copper behind, produces water, which can be pumped out. And once you have pristine surface of copper, then you send hydrocarbon in a very controlled way using this mass flow controller. And that hydrocarbon splits into carbon and hydrogen. Those who know chemistry would know that copper and nickel are the best catalysts for splitting hydrocarbon. So it will split. Somebody is already looking into the watch. So perhaps if my talk is getting a bit boring, but it's all right. So this splits into carbon and hydrogen, and if you maintain right partial pressure, you will get graphene. If you did not maintain, you can get diamond, you can get carbon nanotube, you can get carbon soot. These are all electrons of carbon. So that's how you develop graphene on copper and nickel, specifically on copper and nickel because they are the best catalyst for splitting hydrocarbon. Okay? So there is metallurgy there, there is chemistry there is chemical engineering there. Okay? There is physics there. So, between copper and nickel, yes, both are good for developing graphene, but mechanism of developing graphene on copper and nickel is interestingly entirely different. Reason is that copper has almost zero solubility of carbon, so that carbon that you developed or that you generated because of splitting of hydrocarbon will not diffuse into copper because it has zero solubility. So as long as you generated or created right partial pressure, you will straightaway develop graphene. Whereas nickel has huge solubility. See, copper has very little, nickel has huge solubility. So if you have thin sample of nickel, carbon will diffuse into it, it will saturate. As you decrease temperature during cooling, then solubility decreases. So excess carbon will be diffusing to the surface and it will deposit as graphene. Right? So that's the mechanistic difference. And remember that copper has zero solubility of carbon. The first work on this topic, I will take another 30 minutes or so, or 25 minutes or so. Okay? I will try to be quick. Is that okay? So, thank you. So it's a nice lady, very cooperative. So See, first work on this topic was done by Rod Rook when he was in Texas. And what they did, that they took copper nickel, pure copper nickel alloy, and graphene coated copper nickel alloy and graphene coated copper, and they exposed it to air at 200 degrees Celsius. Copper and copper nickel alloy changed in color because they oxidized, whereas the graphene coated ones didn't. That showed for the first time that graphene can give corrosion resistance. Also what they did, they took a penny, American penny, and they coated only the upper half with graphene and lower half was bare. They dropped into highly oxidizing hydrogen peroxide, and they found that upper half that was graphene coated did not corrode much at all. Lower half was tarnished because graphene was not there to give protection. We were perhaps the first people to work systematically as a corrosion scientist on graphene coated copper, and we published this paper, which happens to be one of the most cited papers on graphene coating for corrosion resistance, nearly 600 times. But the work was done because of a Malayali, PM Ajian, not Ajian Vinu, PM Ajian from Rice University is the world expert in the area of 2D materials, all those 2D materials, chalcodonides and HB and all that Dr. Philip talked about. So he's world expert. His H index is 215. Okay, so he's a very proud son of Kerala and India and IIT BHU. So Ajian, very good friend of mine. We are in fact publishing, working on another paper right now. I met him in Ajian Vinu's conference in Newcastle in November last year. So he sent graphene coated copper and pure copper samples. So once we got that, the first job was to find out whether what we got was graphene or not, and that's where Raman spectroscopy comes in picture. So Raman spectrum for our sample gave this particular type of spectrum, and here you have this G peak and you have 2D peak. Once you have these two peaks, you can be sure that you have graphene if they are at right place, okay? And these two peaks confirm the presence of graphene, but also the relative heights of these two peaks gives me number of layers of graphene. For single layer graphene, G peak is always dwarfer, shorter compared to 2D peak. As you increase the number of layers, you can see G peak becomes taller and taller, okay? For single layer graphene, G peak is shorter compared to 2D, and for 2 and more layers, see. So by the relative intensity of these two peaks, I can tell you what is the number of layers of graphene. So we had single layer graphene because G peak is dwarfer, and D is for defect, one defect. Of course, the pure copper did not have those peaks. When we did that corrosion test that I showed you earlier, is something like seawater, 3.5% sodium chloride, you can see the corrosion resistance improved by 2 orders of magnitude. So one single atomic layer thick graphene improved corrosion resistance by more than 100 times. Single atomic layer thick. And we confirmed that also by EIS, electrochemical impedance spectroscopy. When we were doing this work, around the same time others were working on this topic as well, we were getting more than 2 orders of magnitude improvement. Someone was getting just 1 order of magnitude, and another group from within my own university, Australia, they were not getting much improvement at all. So, you could say, gee, we produce best graphene and we are the best in the world. I think there are quite a lot of students here. It is a message for students. The research is not about showing we are the best. Research is about understanding why we were getting and they were not getting so much improvement. That's what is research, systematic understanding of that, and that's what we took the task to do those kind of things. Now we were actually showing that very good improvement, not good improvement, and all that. Around the same time, 2 papers came. We published that paper I was talking about in 2012. In 2013, a paper came and you will see what the paper was telling. Graphene coating, in fact, accelerates corrosion. We have talked about improvement there. And it was published in a very reputable journal, ACS Nano, very good journal. As if one was not sufficient, there was another paper on the same journal, same year. Read the title, I copied the title. Graphene as a long-term metal oxidation barrier, worse than nothing. It means if you don't have coating that gives better corrosion resistance. Now, this is the time when my first PhD student joined to work on this topic. And I said that you work in the topic. His response was, are you trying to kill my career? There are two papers in the very reputable journals, they are saying this bloody useless thing. Why the hell you want me to work on that topic? So I had to use, I have gray hair, so sometimes experience counts. So I told him this. As a matter of fact, what I told is true, and every researcher should take this into account. Research is not about getting fantastic, best results which will change the world. PhD research is about deriving a hypothesis, planning experimental or theoretical work, and proving or disproving your hypothesis. As long as you did it systematically based on fundamental principles, you had a very good training, you developed an analytical skill. That's what is real. When I told this to him, finally I convinced him, so he continued to work, and you will see who this person was. The problem with these people was that it was not the graphene which was not able to give very good corrosion resistance. The problem was with the quality of graphene they were developing. They didn't see that wherever they had good quality graphene intact, corrosion resistance at that location was good. That they had this problem, they had disruptions in the graphene, and that was causing problem. And we had mentioned that in our paper just here before, we said, if graphene coating is not continuous in the bare area, there is bound to be accelerated corrosion simply because graphene is the most cathodic material. You attach it to any other material, any metallic material, it will force it to corrode, and that's what was happening. So those disruptions are not the only problem. Those disruptions I showed you here are not the only problems with graphene. Graphene also has a problem of developing wrinkles. When you try to develop graphene by CVD, invariably you have wrinkles because, for very interesting physics, graphene is one of the few materials which has negative coefficient of thermal expansion. What it means is, when you cool from CVD temperature, it expands, whereas metal underneath contracts, and that adds to development of wrinkles. But these wrinkles are bad for corrosion resistance because at the top of the wrinkle, the stress can be so hard that it can crack, graphene can crack, and people have shown that corrosion attack happens only at the locations of wrinkles. So what I showed you is that graphene can have those disruptions, those bare areas. Graphene on metal can have those bare areas. It can have wrinkles. It can have one defects. In place of hexagon, it can have heptagon, it can have pentagon, and all those defects are bad. So this is when this man, Abhishek Tiwari, joined, and I did all those convincing, and he said, look, problem is because of those disruptions, because coating is not continuous. How do we address that? Address that by having continuous coating. I can tell you it is almost impossible to have continuous coating by CVD on large surface. At the end of the day, it has to be on large surface for industrial application. How else can we develop that problem? So we came up with this hypothesis that in place of single layer graphene, if I have multi-layer graphene, then the defects in the first layer can be masked by upper layers. That's simple. I'm not a very intelligent person, so I just give simple hypothesis. Okay? And that's what we started with. In fact, we showed that if you have multi-layer graphene, the wrinkles in the earlier layer or lower layer were masked by upper layer, which may itself have wrinkles. So we managed to develop using our own setup, very poor quality graphene. You can see T peak is very tall, but it's multi-layer graphene. G peak is taller compared to 2D, and that graphene gave corrosion resistance by about 10 times, not more. It was not as good as the graphene that we got from Ajay's lab, but most importantly, that corrosion resistance lasted for the entire test duration. For the first time, we addressed the problem. We understood where the problem was in those papers published in very reputable journals, ACS Nano, and we addressed that, and then we showed that graphene that we developed would give long-term corrosion resistance for the first time. Thereon, we started to work on developing multi-layer graphene, and if you remember, I told you that it is easier to develop multi-layer graphene on nickel for those mechanistic reasons. So we worked on improving the process parameters, and one of the parameters we controlled was that two parameters. One was that cooling rapidly after CVD and also without hydrogen in the environment. So those were the two things. Hello, how are you? Good. So we developed graphene. During development of graphene, we had rapid cooling and also without hydrogen in the environment. Okay? And that graphene had very less wrinkles. We did down spectroscopy and all that. And that graphene gave very good corrosion resistance, as you can see, graphene coated nickel with rapid cooling without hydrogen, not much corrosion, whatever white spots you see there, solidified sodium chloride, but corrosion resistance was very good. As you can see here, it was also long-term corrosion resistance. We did test in this corrosive environment for over 1,000 hours, and there was no deterioration in corrosion resistance after initial drop. It was very stable. It is statistically proven data. Can we use this for any practical application? And one of the applications is to use graphene as bipolar plates in proton exchange membrane fuel cell. Okay? These bipolar plates operate in highly acidic environment, and it has very demanding requirement. That's why people use very exotic alloys, titanium alloys, super duper stainless steel and all that, super duplex stainless steel and all that. But even those alloys do not function properly because they undergo corrosion in this kind of environment, and the corrosion film that you form is at the best semi-conducting, whereas the bipolar plates have to be conducting electrically. Graphene gives advantage. What advantage? That it not only gives corrosion resistance, but it's also conducting. Somebody can argue that its conductivity is very good in plane, but we are talking about across conductivity. That too is much better compared to the semiconducting film that we do. So this was published once again in these reputable journals, and you can see that corrosion resistance was very high, but as I said, corrosion resistance was not the only criteria, it was also conductivity, we showed it long term. Then, I talked about this earlier already, if you choose proper nickel copper alloy, then you have graphene coating which has very impressive corrosion resistance, as we showed here. So what I showed you so far, I will take another 5 minutes and finish. What I showed you so far is that you could develop multi-layer graphene on copper, nickel alloy, and showed how corrosion resistance can be improved of such graphene coated material. But the challenge is whether I can develop graphene on larger surface. And second challenge is whether I can develop graphene on mild steel, as I said earlier. That's what is the rest of the talk about. So we started to work on CVD parameters a bit further. What we found, and we are still working on CVD parameters to make it possible to develop graphene on larger surface for industrial application. One of the things that we found is that if we tilt the substrate by 45 degrees, then what happens is that supply of the precursor hydrocarbon that I talked about is far more uniform on the surface. And you can develop much better quality graphene. And seeing it believing, the 45 degree tilted sample did not have much defect in the graphene, very occasional defect, but at 5 degree tilted, which is the same as almost flat, you can see quite a lot of defects. And we did Raman spectroscopy. This is 2D imaging map. You can see that 45 degree tilted and almost consistent Raman spectra at different locations, right? About 5 to 7 layers, 7 to 8 layers of graphene. Whereas the 5 degree tilted had disrupted areas and the spectra were not consistent. At some places you will have 7 to 8 layers, some places 1 to 2 layers, some places even bare. we did corrosion resistance test. You can see that 45 degree tilted had best corrosion resistance even after aggressive. This is a very destructive test. The test that I talked to you about, this PDP, potential dynamic polarization. Even after this destructive test, graphene is still intact if you have 45 degree tilting, whereas 5 degree tilted had graphene coating with lots of disruptions. We use this spectroscopy for the first time for corrosion research. This is scanning photoelectron microscopy, which is nothing but XPS, X-ray photoelectron spectroscopy. But here we are able to do imaging of the surface. So 5 degree tilting, as I said, it has lots of disruption. Where you have disruption, you are getting nickel signal and not much carbon signal, because nickel was there, it was reacting with sulfuric acid, that's why sulfur signal. Whereas 45 degree tilted, you see no nickel signal, not at all. Carbon is very uniformly distributed, unlike what you saw in 5 degree tilting. No sulfur because nickel was not there, so there was nothing to react with sulfuric acid. And again, it was published. So coming to the last part, 3 to 4 minutes, can we develop graphene on mild steel? And answer is straightway no. And it has a very fundamental physics or metallurgical reason. Those who know the phase diagram of iron and carbon will tell you that steel or iron is face-centered cubic structure at 1000 degrees Celsius. And same material has body-centered cubic structure at room temperature. So what's the problem? Problem is, if you know the phase diagram, the face-centered cubic structure has about 100 times greater carbon solubility compared to body-centered cubic structure. So at the temperature where you do CVD, you will have your steel absorbing lots of carbon because solubility is 100 times greater. But when you cool down after CVD, all of a sudden it will reject too much carbon because BCC has only 100 times lesser solubility, which is about 0.02% or so, whereas in FCC has about 2.14%. So during this phase transformation, lots of carbon will be suddenly rejected. And you remember I said that you need controlled supply of carbon for developing graphene. So that proposition will be defeated. And that's why it is almost impossible to develop graphene on mild steel. But if you manage to develop, as I said, it's a non-trivial task, not easy to accomplish, but if you manage to develop graphene on mild steel, it's commercially hugely attractive. You don't need stainless steel. Graphene coated mild steel will work much better than stainless steel, and the coating will be everlasting. Good news is that we have done that. I will be a bit quick. So how did we solve this problem? Very simple. As I said that I'm a very simple person. I don't come up with very big ideas. Just put a thin layer of nickel on top of stainless steel by additive manufacturing, by electroplating of it, and then you develop graphene. Very easy, because we have shown that graphene can be developed on nickel. So put a thin layer of nickel. So, see what is it? It is obvious, but it was unsuccessful. Why it was unsuccessful? We put a thin layer of nickel on mild steel, try to develop graphene, it does not work. Why it does not work? Again, for a very simple metallurgical reason. The nickel that you would like to get into the position where it is saturated with carbon, that you can never achieve. Because the carbon that you have in nickel layer will leak into mild steel, because mild steel too has high solubility. So all the carbon that you wanted for developing graphene would be leaking into mild steel. And because of that reason, it did not work at all. It looked very simple, very obvious, but it didn't work. How do we solve the problem? I had already told you the way to solve it. Say that copper has almost nil solubility of carbon. I said earlier, remember? So first put a layer of copper and then put a layer of nickel. Now the carbon in nickel will not leak into, because it cannot diffuse into copper. I have intervening layer which will not allow leaking of carbon. So we just put a thin layer of copper and then put thin layer of nickel. It did not work again, because we were in a hurry. We did not do proper scientific, we did not adopt proper scientific way, because the time temperature window of CVD was such that during that time, iron will diffuse through copper and through nickel come to the surface. Copper will diffuse through nickel come to the surface, and it will geopardize, it will spoil graphene development. So what we needed to do was this. First do the diffusion calculations and make sure in the time temperature window of CVD, they should not diffuse to the surface. That's what we did. So when we did diffusion calculation, we found that the thickness of the copper layer should be about 10 to 12 micron, we made it 15, and then you have nickel on top of that. And then we did CVD, it beautifully worked. It was on the basis of scientific understanding, right? And you can see it is beautiful multi-layer graphene, not much defect at all. You have multi-layer graphene that gave very good corrosion resistance. I won't go into the details of analysis. And that graphene gave corrosion resistance that lasted for 1,000 hours. It is statistically proven data, much better compared to mild steel or even nickel copper coated mild steel. It is everlasting coating. Why I'm saying everlasting? Because a coating will degrade only mechanically. It will not, because I said that graphene is very tough. Coating will degrade only by chemical attack. I showed that graphene does not react even with hydrogen fluoride. It is chemically inert. Coating will degrade because of diffusion of corrosive species through the coating. I showed that graphene is impermeable. It's only material which has all those properties in one material. It is mechanically so good that if you have graphene coated metal, you bend it by 90 degrees, graphene will bend along with that. It will not disrupt. It has such a good toughness, right? So on that basis, I didn't have time. I don't think that I will live long enough to do everlasting tests. But I don't have any reason against the statement that why it should not be everlasting. So that was my last slide, but I have one more. And it was published, as I said, in these two prestigious journals. And also one more paper is coming this month on this topic. There have been a few partners in this crime, as they say. Tanuj Joshi is currently working on improving the CVD parameters. If I can say, we have solved the science part of the problem. We have to solve the engineering part. That is how we can develop graphene on larger surface. Okay? And Tanuj is working on that. Nikita is completing PhD under the joint program of Monash with IIT Bombay with Subbu. He had just completed Abhishek had just completed PhD degree. We saw his work on tilting. Sanjeev, Anisur, Abhishek were my PhD students on graphene. Others were also PhD students, Lokesh, Karma, Rachel, but they were not working on graphene. They helped in the first paper, they were part of the work. Manak is a professor now, he was junior academic when we started to work on this topic in 2011. The last 5 people are very important. They are all final year project students, they are undergraduate students. So my first paper, which has been cited nearly 600 times, it was done as final year project work. Okay? And first samples, as I said, came from my friend PM Ajjan's group, Rice University, and it has been a great success. This entire work was accomplished without any funding from any government agency. The only thing I got was a little bit of money from Monash University and PhD students fully supported by Monash University. So I hope that I did present to you a convincing case that because of some intuitive application of metallurgy and understanding of the problems with the graphene earlier, we could achieve something that is disruptive, that is everlasting coating due to very thin graphene layer. Some of the questions that I have when I give this talk, I've given this talk a few times, is that, is it expensive? It is not. Because graphene is new, you think that, oh, it must be expensive. The chemicals are hydrogen, methane, cyclohexane, not at all expensive. But achieving right engineering situation where the graphene can be deposited on larger surface. That's something that we are working towards, and hopefully next time when I come to this beautiful Kerala, I will be able to show you those results as well. Thank you very much. I thought that I was the only unique person in this hall because I took liberty, or perhaps I was ignorant to come to the hall with shoes. But the latest person also has come with shoes, so I don't feel as guilty. That's all right. No, you don't have to feel sorry. I have done the same. I've committed the same crime. Yeah. Thank you.
Dear Dr. Raman Singh, ICAMS-2025 is deeply grateful to you for your presence and eloquent presentation here. We are fully aware, sir, we cannot thank you enough for all the efforts you have put in to be with us today. And we are well aware and sure that all our participants are deeply inspired by the way you presented this topic of relevance to all of us. May I, on behalf of the entire team of International Conference on Advances of Material Science 2025, extend our deepest appreciation and gratitude to you, Dr. Raman Singh. Thank you so much. As a symbol of our deepest appreciation and gratitude to Dr. Raman Singh, may I request Sri Nelson sir from the Department of Physics, Assistant Professor of the Department of Physics, to present the memento to Dr. Raman.
Very, very right person to give you the memento. But before that, if time permits, if anybody has any question, really, I'm happy to answer. Yeah. Do I have time? I can't take liberty. The chairperson decides. Can I answer questions? Yes. Okay. Yes. Yes, sir.
I'm very sorry at first to come late, but in the remaining part is very interesting for me.
So first part was boring, I can tell you.
Because I was absent. Sorry once again.
Don't worry. Yeah, question is,
Professor, graphene is the most needy materials nowadays, especially for those who are purchasing new vehicle here, because here the climatic condition is changing like anything. In graphene coating, first you are applying on the surface of a car, etc. They ask to preserve it in air-conditioned temperature at least for 72 hours. Of course, it is temperature dependent.
Okay, I got your question. In fact, what you are saying is a bit different from the talk that I gave, even though both are graphene. When it comes to use of graphene for corrosion resistance, there are two distinct paths. What I presented is direct pristine graphene G on metals, okay, by CVD. What people who are using graphene for paints or on the car, they are using graphene's derivative. They are using graphene oxide, and which is not generated by CVD. They are generated by chemical routes, right? Graphene oxide, which is reduced to make it RGO, and why it is not called graphene oxide is oxidized form, and if you reduce it should be G. No, it is not called G. It is always called RGO because you can never completely reduce it. At the edges, as Professor Philip said, you always have functional groups like carboxylic group, hydroxylic group, epoxy group, and all that, and you functionalize that for binding with the paint. So when you because graphene is planar, they are platelets. When you incorporate that into paint, they act as agencies that create tortuous path for corrosive species to get through the coating, and that's what Tata Steel has done. Tata Steel has done, and that kind of coating requires what you are saying. That's graphene true, but it's graphene oxide. Now your question will be that why don't we just paint graphene on metal? Why take the trouble of doing CVD? reason is that when you do CVD, because you came late, what I presented is by passing hydrogen during CVD, you are getting rid of the native oxide layer, which is very important. The paints fail also because that native oxide layer is attached very quickly. But by CVD graphene, you are getting rid of that. That's why it is disruptive. By having paint, yes, it is normal polymeric paint, whose properties you have improved by incorporating the derivatives of graphene. So that's the difference between the two. Yes, that's what many people have incorporated many things for improving corrosion resistance due to coatings, but that's not disruptive. This is altogether a different approach. I hope it answered your question. Yeah. Any more questions he's asking? No? Okay. Thank you very much once again. I'm very thankful to the organizers and I'm very, very happy to be here. I came with some hesitance because I have been traveling in the last 1 month. I have been to 15 or 16 places. I travel every second day or third day. But I think this is the best part of all those one month of traveling. Thank you very much.
Thank you so much, Dr. Raman Singh. May we now proceed to the presentation of memento. I humbly request you to receive the memento from Sri Nelson Kuriakos. Sir, please. Thank you, Dr. Raman Singh and Nelson sir. Dear delegates and participants, we are now proceeding to a photo session near the registration counter, and thereafter we will be proceeding to have a short tea break. May I request all of you to gather in front of the registration counter right now without any delay. Thank you so much.
ലാസ്റ്റ് കണ്ടോ എടുത്തോ, ലാസ്റ്റ് കണ്ടോ തന്നെ എടുത്തോ. ഞാൻ അയച്ചെന്നവരെ കാണിച്ചില്ല. അതിൻ്റെ ടെൻഷൻ അതിൻ്റെ പോയി മറ്റേ അതുപോലത്തെ വരുത്താൻ പറ്റും, വരുത്താൻ പറ്റും. വരുത്താനൊക്കെ പറ്റും. ഞാൻ പോയിക്കോ, ഞാൻ ചെയ്യുന്നുണ്ട്. പിന്നെ ഏറ്റവും അവസാനം അയച്ചു കൊള്ളാം.
പിന്നെ 1 മണിയായി.
അവസാനം അയച്ചു ഓക്കേടാ, ഓക്കെ അല്ലേ? അപ്പോൾ ഓക്കെ ആയിരിക്കും. ശരി.
including carbon-free hydrogen production and carbon dioxide recycling, and create environmental sensors for monitoring harmful gases and diagnosing diseases. These initiatives are not only designed to mitigate climate change by reducing carbon dioxide accumulation, but also to protect human health and advance medical diagnostics. Dr. Verghese' contribution embody the intersection of science, sustainability, and societal impact. Please join me in welcoming Dr. Umanki Verghese as he shares his insights and groundbreaking research with us today.
Thank you for the kind introduction. Well,
Yes, sir. Yes.
Greetings from Houston. I thank the organizers for giving me this opportunity to talk about my research in the conference on advances in material science. So I congratulate the St. Dominic's College community for the Diamond Jubilee celebrations, and I wish all the best to the all the students there. So today in my talk, I'll be focusing on some of the earth-abundant materials that are used for energy conversion and associated applications. So if you have any questions, you can ask at the end of the presentation, or you can write to me at this email address. So I am from University of Houston. So Houston is one of the fourth largest city in the United States, and it is in the state of Texas. So here you can see the downtown Houston, and here the campus of University of Houston. So the University of Houston has over 47,000 students with science, engineering, and a wide range of other areas of research. So now here in this picture, you can see the football stadium in the university. This is American football, not the soccer that we play in India. So that's all about University of Houston. So if you are interested in applying to for PhD or masters or even undergraduate courses, you can, and if you have questions, you can write to me. I can connect you to the appropriate people. So coming to the topic of this talk, so we all know that there are catastrophic issues due to global warming. And a good example of that is the wildfire in Los Angeles. You might have heard through news that the fire is spreading at an alarming rate. So the global temperature is increasing rapidly, as we can see in this diagram. The carbon dioxide emission is in billion metric tons. That has increased since 1950s, and at the same time, the global average temperature also started increasing. Now the temperature is higher by more than 1.2 degrees Celsius. So it is expected that within 30 or 40 years, the temperature will go above 2 degrees Celsius. That is a substantial increase in the temperature. So the impacts of this increase can be all these are detailed in the United Nations Intergovernmental Panel on Climate Changes report submitted to UN in 2021. So in the atmosphere, we have 3 to 7 billion tons of carbon dioxide that should be removed in every year to reduce the temperature increase. So how can we do that? That is not an easy task. 3 to 7 billion tons of carbon dioxide removal. That can be done only through very systematic ways. So demand reduction is one of the common strategies, but that cannot really bring dramatic changes in the carbon dioxide level. So a shift from fossil fuels to renewable fuel or renewable energy is a very feasible option. In addition to the use of renewable sources for energy, carbon dioxide removal and carbon dioxide capture and storage, or carbon dioxide capture and utilization are some of the strategies that should be implemented for a sustainable future. So in addition to all these changes, there should be technologies to be developed to support the change in the paradigm from fossil fuel-based energy to renewable-based energy. So we will discuss all some of the energy conversion technologies as we during this presentation. So in my laboratory, we have our focus is on developing nanomaterials, especially the semiconducting nanomaterials for energy conversion and related applications. We work on developing one-dimensional and zero-dimensional materials. We can see the nanotubular structures, nanorods, and heterostructures of the one-dimensional and two-dimensional materials, and so on. So all those materials are developed for the purpose of solving the issues associated with the energy and environment. So we will discuss some of these elements and their special properties when these are fabricated in as nanostructures. So this is graphene film developed using Australian tea tree oil. This work was done in collaboration with Dr. Mohan V. Jacob, who is an alumnus of St. Dominic's College. So in Dr. Mohan's lab, they converted the Australian tea tree oil to graphene using plasma assisted deposition process. The graphene developed using this method showed very high hydrophobicity. The theoretical maximum contact angle for water in graphene is around 96 degree. However, we got around more than 135 degree. That is because of the modulations of the surface of the graphene films. Now this material, when we developed electronic devices, we found that it has a memory-resistive properties. That means memory resistance properties. So the device was developed with the pentacene as the semiconductor and the graphene as the buffer layer or conducting layer on a fused silica. So this memory-resistive device can switch the resistance from high resistance to low resistance value repeatably without any degradation over a long time. So continuing this collaborative work, we did we worked on several other organic materials. Dr. Mohan's lab developed graphene films from orange oil using RF plasma. So then here you can see the images of graphene films with nano onion structures. These structures are embedded within the film and was developed during the fabrication process due to the stress developed during the film formation. Now, this when we developed the sensors out of these films, it showed a sensitivity, high sensitivity to acetone. So you can see the variation in resistance of this film when exposed to acetone. The acetone is a biomarker for diabetes, and so this sensor can be potentially used for monitoring the diabetes. So here you can see the film of graphene oxide with a larger interplanar spacing. So this film was again developed in Dr. Mohan's lab using microwave assisted chemical vapor deposition. So here the graphene oxide films are doped with nitrogen for device application. So again, graphene was also developed using microwave plasma at ambient condition using tea tree oil. See, the images are transmission electron microscope images are given here. So this material was used for pesticide detection, especially diuron detection. So these are the technologies that can be used for developing or storing carbon dioxide and then utilized for different applications. So the plants convert carbon dioxide to the organic products, and these process, for example, RF plasma or radio frequency, the microwave plasma can convert this into carbon, and that can be used for devices or can be stored. Now we will discuss the compounds using titanium. So here we can see some of the nanostructures of titanium compounds. So the top images are of titanium dioxide nanotubes fabricated using hydrothermal process. Here the tubes are layered. These can be considered as scrolled layers of titanium dioxide. On the other hand, we can get nanotube arrays if we do the anodic oxidation process on titanium foils. So these tubular structures are vertically aligned, so like a test tubes arranged on a table. So here we can see the tubular structures very closely packed, almost hexagonal close pack with a very high surface area. We can also increase the spacing between the tubes. Here we can see the nanotubes with spacing between the tubes. So we can have different morphologies and different dimensions. Typically, we can increase or change the length of the nanotubes from a few hundred nanometers to several hundred micrometers, while keeping the wall thickness in a 10 to 20 nanometer range. So these nanotubes are made using a process called electrochemical anodization, which is very simple. So we have two electrodes immersed in an electrolyte. With the positive electrode is the material where we need to form the low dimensional structures. So for a titanium anodization, titanium is used as the titanium foil, or a film is used as the positive electrode, and a platinum or a graphite is used as the cathode. So now when we apply the electric field between the two electrodes, the tubular structures or other nanostructures are formed spontaneously on the surface of the titanium foil. So the process is very simple to visualize, but it involves very complex processes within the going on within the electrolyte under the action of the electric field. So the metal is first oxidized under the action of the electric field. So the oxide layer increases the resistance of the the electrode. As a result, the current, anodization current reduces. Now, when we have the species like a fluorine in the electrolyte that can etch or that can create H pits in the film, the oxide film, and this H pits can reduce the resistance, or they can increase the electric field at the interface. So then there the growth will occur further, and also the oxidation happens again due to the electric field action. So the oxidation and the etching happen simultaneously, and so as the tubular structure is formed on the substrate. So these structures are useful for solar energy application. Let me describe briefly the status of the solar energy conversion technologies. So one of the most the commonly used renewable energy conversion process is photovoltaics, or a device is photovoltaics devices. The solar cells convert the solar photons to um, um, the electricity. Now, the solar photons are distributed in the energy range around the 200 wavelength range, around 200 nanometer to around 4500 nanometer. Out of that, the primary region of supply of photons is the visible region. So up to around 1000 nanometer, we get around 58 to 60% of the photon flux. So now the photons are incident, when the photons are incident on the device or the solar cells, it excites the electrons in the valence band of the semiconductor. So the electrons get energy and they go to the conduction band and are available for conduction. Now, there are high energy photons. For example, if you use silicon as a semiconductor with a 1.1 electron volt, there are the ultraviolet photons of energy greater than 3 electron volt. So this can excite the electrons to very high energy levels, but they don't stay there. They lose the energy, or as they radiate thermal energy and then get back to the bottom of the conduction band. So as a result, some energy is lost. And also because of the band gap, there are always some energy is lost because some photons are not absorbed, but they are transmitted. So they are lost. So there are loss processes, and as a result, the maximum efficiency of the solar device, single junction solar device, is limited to around 33%. Now, the current solar cell market, silicon leads the photovoltaic devices. Around 95% of the devices are made out of silicon. So the solar cell efficiency of silicon cells is 26.7% in the lab level, and in the module level, it is around 23%. Now, there are other technologies like a cadmium telluride, copper indium gallium selenide technologies. Those are having lower cost. Those are lower cost technologies, but their market share is less than 5%. In addition to the photovoltaics, we have the option to generate fuels out of solar photons. So the photovoltaic assisted electrolysis is one option where the solar cells can power electrolyzers to split water to generate hydrogen. The other process is to concentrate solar power or solar energy and then increase the temperature to carry out the chemical processes. So those are called thermochemical processes. There we can convert carbon dioxide to fuels, or we can split water to generate hydrogen as a fuel. The third process is photocatalytic or photoelectrochemical process, where we shine sunlight on a semiconductor, where the electrons or in the holes, the positive charge, are generated, and these perform the redox processes leading to fuel generation. That can, again, carbon dioxide can be converted into value-added products like methane, or even methanol, or other liquid fuels or gaseous fuels, or water can be split into hydrogen using this process. Now, when we developed the nanostructures of titanium dioxide first, we found that those were really useful for photovoltaic application, not as an absorber, but as a electron transport layer and a support layer. So what we did was that we took the nanotubular structure, which is very high surface area. That means if you unfold the surface, the tubes, and we can, if we straighten that and make sheets out of that, the surface area we get is hundreds or 1,000 times the actual area it occupies. So we use that as a support for light absorbing chromophores, like dye molecules. Now, these dye molecules absorb light and then generate electrons and holes. The electrons are driven to the titanium dioxide nanotubes, which are transported to the conducting layer, and the holes do the oxidation of the electrolyte. Usually liquid electrolyte is used, and then the electrons are transferred to the cathode. Now, from the cathode. So this is the typical function of the dye-sensitized solar cells. So in order to use the titanium dioxide, so we have to make a transparent layer of titanium dioxide nanotubes, because the substrate here, you can see this nanotube film with the substrate on a substrate, titanium metal. This cannot be used for photovoltaic application because it's opaque. And we found that the opaque, the cells made using the opaque nanotubular films were not really efficient. So we first removed the substrate to make the transparent self-standing layers of nanotubes. Here, these are translucent. These are around 100 micrometer long, the self-standing films of titanium dioxide nanotube arrays. When we made initially the dye-sensitized solar cells using this material, we found promising results. The electron lifetime in this material was significantly higher than the traditionally used nanoparticle film. But again, the process was not easy. Our device fabrication was not easy with the very fragile self-standing films. So then we converted the technology to fluorine-doped tin oxide glass, transparent glass. So we coated the glass with the reflecting film of titanium, and then we subjected this film to anodization. So during anodization, the film became translucent and then transparent. So you can see the transparent film around 0.8 micrometer thick layer of titanium dioxide nanotubes, and these are the electron microscope images of the nanotubes on this glass. So as we increase the thickness, the film becomes translucent, and it can have more surface area, and we have gone up to around 20 micrometers in thickness for the titanium dioxide nanotube layer. So when we fabricated devices using dye-sensitized solar cells using this material, we found that this has promising properties because of the high quantum efficiency in almost entire absorption region of the dye. We used N719 dye with an absorption edge around 700 nanometer, and throughout this range, the quantum efficiency was high in these devices. Then recently we collaborated with the Michael Gratzel's group in Lausanne, EPFL Lausanne, and we applied this material for perovskite solar cell fabrication. So left side we can see the cell fabricated using a nanotube, and the right side is a cell using nanoparticulate film. So in the nanotube film, we have the first FTO glass, fluorine doped oxide glass, coated with a titanium dioxide nanotube film. And this film was filled with methyl ammonium lead iodide light absorber. And then a whole transport layer, which is a spiro, and then on top of that, the conducting layer of gold. So now this is the top image of the methyl ammonium lead iodide on nanotube, and this is on the same material on top of the nanoparticle film. So these devices fabricated using nanotubes, where those devices gave a larger current, photocurrent, and photovoltage. The overall efficiency was 15%. That was highest in such a devices during the time. It was around 9 years back when we did this work. The quantum efficiency was also much higher for the nanotubular film. Now, more importantly, the films were the solar cells were found to be stable when the nanotubes were used. One of the problems with the perovskite solar cells is the lack of stability. With the time, these materials degrade because of the interaction with the oxygen and water vapor, and they lose its solar cell performance. Now, when the titanium dioxide nanotubes were used, the devices retained its efficiency, although there was an initial degradation, but then it was stabilized, and it was stable for a long time. So that property was due to the scaffolding effect of the titanium dioxide nanotube. The light absorbing material was encapsulated within the nanotube, and the nanotubular structure protected the material from interacting with the oxygen and water vapor. Now, coming to the other application of these structures, so we used this material for water splitting and carbon dioxide reduction. So when we have the option of distributing these nanoparticles of the semiconductors in electrolytes, and then shine them with water, with sunlight, and then it can split water to hydrogen by generating the electrons and holes. The electrons perform the reduction process, and holes perform the oxidation process, and the water is split into hydrogen and oxygen. We can do the same with the carbon dioxide, when the carbon dioxide will be converted into the gaseous or liquid products, depending upon the conditions used. This is one strategy. Other strategy is the photoelectrochemical conversion, where we make the anodes or cathodes of or both using semiconducting materials, and then shine them with sunlight. So then the sunlight generates electrons and holes, and then the oxygen and hydrogen are generated in two separate electrodes, because we separate the reduction and oxidation processes in the photoelectrochemical cell. So this is how these fuels are generated. So when we did the initial work using titanium dioxide nanotube, the material was not really efficient in generating fuels because it absorbs only the ultraviolet photons in the solar spectrum. So you doped this material with the nitrogen, so we can see the greenish color of the film. That is because the absorption rate shifted from 400 nanometer to the green region, as evident from this graph. So this material started absorbing the solar photons in the visible light region, and when we used them as a catalyst in a reactor, um, then we got the methane when the material was illuminated with the sunlight. The reactor was filled with the carbon dioxide and water vapor. So after the reaction, the methane was detected within the reactor. So we used copper and platinum as the co-catalyst for this reaction for a sustain. Recently, we had a collaborative work with Rice University, Professor P. Ajay's group in Rice University, and Professor Anandaraman's group at Cochin University. So the iron oxide is a semiconductor with a band gap of around 2.2 electron volt. But this material is not really an efficient electrode for solar fuel generation because of the very small diffusion length of the holes in the material. The charge transfer properties is very bad in this material. So in Rice University, they exfoliated iron oxide, the hematite, to a new material called the hematine. So the hematine is a two-dimensional layer of graphene of iron oxide, similar to graphene, but this is not a completely two-dimensional layer, but it has the unit cells of 1 or 2 unit cells of iron oxide. So hexagonal structure of the lattice is evident from this aberration corrected transmission electron microscope images. So what in our lab, what we did was that we use this light absorbing material to absorb light, but for charge transport, we used a titanium dioxide nanotube. So we created a heterostructure of iron oxide and a titanium dioxide nanotube, so that the iron oxide or hematine, the two-dimensional material, could absorb sunlight and transfer the charges efficiently to the titanium dioxide nanotubes, so that we can split water or convert carbon dioxide to fuels. So when we did the quantum efficiency measurements, we got an elevated quantum efficiency in the visible light region that clearly shows that the iron oxide was absorbing light and transferring the electrons to the titanium dioxide band gap. But when we did the more fundamental studies, we realized that the efficiency was not really high. That is because there is an inappropriate band gap or mismatch between the conduction, the band and of the iron oxide and the conduction band of the titanium dioxide. Because of this mismatch, the electrons are not really cannot be easily transferred to the titanium dioxide nanotube because it is an uphill process. So that means we are getting high quantum or reasonable quantum efficiency in the visible light region due to the hot electron transfer through this from this two-dimensional layer to the titanium dioxide nanotube. Now, when we replaced the hematine with another material called boron nitride content dot. This also was developed in Dr. Ajay's lab in Rice University. So they created this content dots of boron nitride and then fluorinated it. So as a result, the band gap of the boron nitride is a wide band gap material, but as a result of fluorination, the band gap became narrower, and so it could absorb visible light. So here we can see the quantum efficiency of the electrode, the photoanode made using titanium dioxide and boron nitride. So there is a enhanced quantum efficiency up to around 25% in this material. So when we use this material for water splitting, so there is a significant increase in the hydrogen generation rate compared to the rate we obtained using bare titanium dioxide nanotubes. Now, let me discuss briefly some results that we got recently on a specific property of these nanotubes. So we did simulations, Monte Carlo simulation, to see whether the nanotubes could be used for steering the very high energy ions through them. So that process is called ion channeling. Normally, this is done using the interplanar spacing in the single crystals such as silicon. So now, the advantage of using nanotube is that we have a very large diameter, so we can steer the high energy ions better through these nanotubes. So when we did the simulation, what we observed was that as the high energy ions of helium, around 1 mega electron volt, as they enter the nanotubes, the ions become ions move in a spiral shaped trajectory and then come out of the other side of the tube. That means it is channeling, the ions are channeling through the nanotube structure. That is because of the repulsive potential at the repulsive force exerted by the walls of the nanotube. Now, because of that force, the ions are suffering the focusing effect. So you can see here the focusing of the different the beams of ions. The multiple foci are formed within the nanotubes. These are nodes. You can see the nodes or focal regions here, where the different beams are focused, and these are antinodes where they are farther apart. So the focusing can be done outside of the nanotubes also. So the high energy ions emerge out of the nanotubes, and then we can focus them to a single point. Normally, this focusing needs very high magnetic field, several Teslas of magnetic field to accomplish this. However, because of the repulsive potential or repulsive force at the walls of the nanotubes, we could accomplish the same effect using the nanotubes. These tubes, if you bend slightly, the beams also suffer bending. Not too much, but up to around 1 degree or 2 degree, if we can bend the tubular region, and the ion beams also follow this similar trajectory. Now we briefly discuss tungsten as another material, which is again abundant material. So one of the devices, one of the applications we tried was phototherapy of cancer using ammonium tungstate nanorods. So we developed ammonium tungstate nanorod using hydrothermal process. These are ammonium tungstate nanorods, and we used that for photothermal therapy. So what it does is that it absorbs the photons in the near infrared region and increases the temperature locally. So if these particles are dispersed near the cancer cells, it can absorb laser light in the near infrared region and increases the temperature. Here we can see an increase in temperature to up to around 60 degree when these rods were exposed to 2 watts per centimeter square laser beam. Now, we when we did the experiments, we found that this material could destroy the breast cancer cells through photonecrosis. The upper images show the cancer cells without any ammonium tungstate. These were illuminated with the same laser beam, but the bottom part shows when these cancer cells were in the proximity of the ammonium tungstate nanorods. These these red cells are dead through those are destroyed by the ammonium tungstate through photonecrosis. So this is could be used for destroying cancer treatment. So we also developed porous tungsten oxide and tubular tungsten oxide using anodic oxidation. So here we can see the porous structure of the tungsten oxide film fabricated using anodic oxidation. So it is not an ordered pore, but we use them for water splitting. If the photocurrent generated was not high when we use this material, so primarily because the thickness of the layer, the porous layer was too small, and there was a dense layer underneath the surface. So the surface area was not very high in this film when we used 10 volt for anodization. Now when we increase the anodization voltage to 20 volt and 40 volt, we got better nano structures and even nanotube-like structures, and the photocurrent increased above 1 milliamps per centimeter square. So we could actually increase even further when we developed nanotubes of this film using anodic oxidation. The last, let me discuss the material zinc. We developed zinc oxide nanotube nanowire hybrid architecture, again using anodic oxidation. This material was developed for the purpose of making sensors for medical diagnosis. We developed breast cancer volatile organic compound detectors using this material. When the body has diseases like a cancer, the stress developed within the cells enable the production of volatile organic compounds within the cells. These volatile organic compounds are transferred to blood, and then they come out of the lungs. So the exhaled blood has volatile organic compounds. Those are biomarkers of cancer. But the challenge in detecting them is that they are in very small quantities, parts per billion and parts per trillion levels, and also the number of compounds that is very high, hundreds or even 200 volatile organic compounds can be found in the breath, and finding the exact biomarker is a really difficult task. So that is why we developed the nano materials, the nanotube nanowire architecture could enhance the sensitivity to these biomarkers. So we found that this material could respond to volatile organic compounds of breast cancer, the acetophenone, isopropanol, heptanal, and isopropyl myristate. They are in parts per million or parts per billion levels, but our sensors could detect that. And the response was very repeatable. We can see the resistance variation. When we expose the material to volatile organic compounds, the resistance goes down. And when we remove the VOCs in air, it goes up. So it can be cycled. So there is without any degradation. Now, I'm going to discuss a few, in a minute, I'm going to discuss some work we are currently doing, which are unpublished. I would like to stop any recording of this part of the talk because these are unpublished. I appreciate if the recording is stopped for the rest of my talk. So we use simulations such as finite difference time domain method to understand the propagation of the electromagnetic waves through nanomaterials. And this information is used for
Dr. Margit, are you able to hear me?
Yes, I can hear.
Yeah. Raman Singh is my name. I come from Monash University in Australia.
Yeah.
So I'm physically here at this conference, and I'm very happy that I'm here. I have one simple question. Please ignore if it is too simple and silly. My question is that when you have T3 oil and you do microwaving to produce graphene, that's what I understood. Is that right?
Yeah.
What makes it possible to develop complete graphene by not other crops of carbon, like carbon nanotube, or carbon soup?
Yeah. So that depends upon the substrate and the growth condition. So it is actually possible. So the work was done in Dr. Mohan Jacobs' group in James Cook University, Australia, the film deposit. But I can explain the process. So when we can tune the plasma condition to make the carbon atoms deposit on the substrate. So it depends upon the substrate as well as the growth condition, especially the temperature. For the plasma-assisted, radio frequency plasma-assisted deposition, the temperature should be very high, 700 or 800 degrees Celsius. So that condition, the feed, the gas, the organic material can be cleaved, the bonds can be cleaved, and the carbon can deposit as atoms on this substrate. If those are deposited as atoms on this substrate, most likely it forms a two-dimensional film. On the other hand, if the growth takes place in the three-dimensional, it can be smooth or it can be a particulate that can be easily detached from the substrate. So now in the microwave, they could do even at a room temperature or atmospheric pressure because the energy supplied is different through the microwave process. The cleaving process is different with the microwave.
Yeah, thank you very much. If I will take it a little bit further, in every case, you are producing atomic carbon. What is the factor that decides that each atom should organize themselves as two-dimensional graphene as opposed to diamond, which is three-dimensional, or even carbon nanotube or so? What is the factor that decides?
So so I would say everything is controlled by the energy. Okay. So where the lowest energy, that is what is preferred under equilibrium conditions. So the substrate gives an opportunity for the reaction to take place in a preferred direction. So that is why it is done. It can be. So if you change the condition, and then the particulate will be formed, and so that there is no two-dimensional growth. Instead, the atoms will stack and form the film. So that actually happened in their work also. The powdered films were formed under different conditions. But at optimal conditions, the energy the most stable configuration is the film, and that is adherent to the substrate. And so the details, the theoretical details have not been calculated. what is the energy required and all those things, that has not been calculated.
Thank you.
Thank you, sir. Thank you very much, Dr. Ume Verghese, for your enlightening presentation and for sharing your groundbreaking research on nanomaterials and their transformative applications. Your work in developing sustainable solutions for energy and environmental challenges is both inspiring and crucial for a better future. We truly appreciate the depth of knowledge and innovation you have brought to this session. Thank you once again for your time and valuable contributions.
Thank you very much.
So now this is time for lunch break. Please gather back soon after the lunch within 2 o'clock.
Center for Medical Innovation. Dr. Radhakrishnan completed his PhD from Rajiv Gandhi Center for Biotechnology in 2008 and postdoctoral studies from the University of Tokyo in 2010. With 13 years of research experience, he has published 162 research papers, 38 chapters and 3 review papers. His research focuses on translational applications of plant microbe interactions, antimicrobial resistance, microbial natural products and nanocomposites for food packaging and medical applications. His expertise has been recognized through various awards and honors, solidifying his position as a leading researcher in his field. We are so happy and grateful to have you with us. I humbly invite Dr. Radhakrishnan for the presentation.
Is it okay, the audio and the video? Hello, am I audible?
Yes, sir.
Shall I proceed?
Yes.
Whether the slides are visible now?
Yes, sir.
Okay. So first of all, I express sincere thanks to the organizers for providing me an opportunity to present some of our research findings and also to keep us in part of this particular program. And the topic of presentation is on nanomaterials for antimicrobial applications. And as we know, antimicrobial applications of nanomaterials, this is a highly demanding area because of many reasons, mainly the health challenges or diseases which are caused by various pathogenic microorganisms. And when we consider the pathogenic basis or virulence basis of the same, some of the basic issues that are challenging include the so-called biofilm formation by microorganisms and the antibiotic resistance by microorganisms. So biofilm here means a group of microbial cells can get connected together or will be kept under a common extracellular matrix, so that the materials which are given in the form of drugs for the management of these organisms may not act effectively. And just like that, the antibiotic resistance is another major issue. And here, even though we are using variety of antimicrobial agents for the management of pathogenic microorganisms, there are emerging concerns with antimicrobial resistance. And the image given here is taking you through an overview on so-called identification and characterization or clinical introduction of various drugs in the form of antibiotics. And as you can see that even though various chemicals, in the sense antibiotics, are introduced, the parallelly what happens is the multi-drug resistance emergence is also happening along with pathogenic microorganisms. So it will take almost 20 to 40 years for the clinical introduction of a particular drug for the management of a particular pathogen. But for the microorganisms, it's a matter of days or weeks to get resistance to against these drugs that we are using. So the major limitation here with respect to antibiotic is that most of the antibiotics are acting at a particular site within the organism. So they are highly specific to particular target. So because of its specific mode of action, the microorganisms are able to develop or evolve or become resistant to this one by changing its target in various ways and through the so-called drug resistance mechanisms. So this is a major concern where the role of nanomaterials or nanotechnology is becoming more important, because as we can see that as per the emerging reports, along with other diseases that are there, the death due to antimicrobial resistant pathogens are becoming more. And even most of the cases, we are not at all having an awareness on the same itself. Because, for example, in the case of COVID condition or other conditions where the patients are in the ICU or under ventilator stage, most of the times what happens is that during the hospitalization, they will get exposed to various types of pathogens within the hospital, and the treatment of such organisms will become more difficult, and the final death can be due to the organisms which might have introduced during the subsequent stage or secondary stage instead of the primary infection which is caused by another organism. Because once it is into hospital, if it is antibiotic resistant organisms, the treatment is very, very difficult. So that is a major concern. And this is a particular example. First part, I am presenting some details about so-called coagulase negative staphylococci. These are so-called commensal organisms present in human generally, because these are present in different parts of the body, especially on the skin and other parts. And generally, they do not have any pathogenic concern, or they are not at all problematic. And but if it happens to enter into human, they can change their lifestyle from a commensal mode to a pathogen. So that is very, very important. And how it happens, because as you can see, some of the clinical conditions images here, like infected heart valve, like healthy heart valve you can see, and at the same time infected valve image is there. Then osteomyelitis, septic arthritis, some examples are given. And another examples include wound and joint infection and intravascular catheter infection, urinary tract infection. In most of these cases, one important concern is with respect to the use of so-called medical devices. And these medical devices are used routinely for various purposes. But the problem what happens generally is that during the time of insertion of this medical device into the body of particular patient, at the time of this device insertion into the body, the so-called commensal organisms which are present on the surface of the skin can get attached to these medical devices. And once they are into the body, the organism will attach on the surface, will multiply and result in the formation of so-called biofilm. And such biofilm mode of growth can provide survival advantage to the organism, and thereby the person become infected, and thereby the clinical conditions may happen. This is a serious issue because catheterization sites in human body can be at any site, as it is mentioned or like it is indicated in the figure. Whether the figures are clear, whether the slides are moving. Hello?
Sir.
Yeah, is it okay that the slides are moving?
No.
Hello?
Yes, sir, the slides are moving. Can continue.
Is it okay that my is it audible also?
Yes.
Okay. So this particular issue is a serious one because, as you can see, that the site of a catheter insertion can be at any parts of the body as per the requirement, as per the clinical condition, as per the particular disease, and so on. So this is a routine practice which is being carried out in the hospital. And this is how the biofilm formation happens. As you can see that this is a insertion of a particular medical device into the body, and these organisms which are commensal, which are present on the surface of the skin, and when they are present on the surface of the skin, they are harmless, they are just present on the surface. But once they get attached to the so-called medical device, what will happen is that they will multiply on the surface of this device and form the so-called biofilm, so that large number of organisms will be formed. And this is how the process takes place. That means initially the organism will come and attach here, gradually it will multiply, result in the so-called biofilm structure, and later the lysis of this biofilm structure can take place, and thereby the release of organisms into the bloodstream, so that the organism will get transported through the blood and will be deposited wherever the blood goes, and wherever the organism is attached or deposited, there it will again multiply and it will result in the formation of a particular disease or a clinical condition. So this is a major issue. And here comes the relevance of antimicrobials in the form of nanomaterials. And the major attraction with respect to nanomaterials for when compared to the antibiotics, it is the major advantage is because of their multi-targeted action. As I mentioned earlier, antibiotics are acting at specific target, but nanomaterials are not site-specific because it can act at various sites in the microorganism, so that it will not be that much easy for the organism to develop resistance against nanomaterials when compared to its resistance against the so-called antibiotics. The image given here indicate the various sites of action of commonly used nanomaterials, including various types of metal nanoparticles mainly. And at the same time, we are into a area where many of the items, whether it is healthcare products or other products, they are all getting labeled as nano-based, and this indicate the emerging demand and emerging application of these products in this type of nanomaterials in various products. And first, I will share some details about synthesis of gold nanoparticles that we carried out, and then about silver nanoparticles. And here, this is about the silver nanoparticle synthesis. In this one, we have used specific bacterial strains for the synthesis of nanoparticles. And this is as you can see, this is a particular organism used, and this is a nanomaterials agglomerate, means getting accumulated in the culture medium. So you can see the nanomaterials by synthesized by different organisms. And these nanomaterials were further evaluated for their antimicrobial mechanism, and this is basic antimicrobial activity against the so-called coagulase negative staphylococci or commensal organism. And you can see here the zone of inhibition around the well, which is due to the antimicrobial action of the nanomaterial synthesis in the study. And this is an activity of a gold nanoparticle. When compared to the silver nanoparticles, here we could not find that much effective activity as that of silver nanoparticles. And this is the various types of analysis that we carried out to confirm the death of the organism due to nanomaterial interaction. And here the control Staphylococcus epidermidis, and that one treated with the silver nanoparticle is given, where the cell's viability, loss of viability is indicated by the color or red color here. And this is the AFM analysis, which indicate the description of typical bacterial structure. This is a control and this is a treated one. We can clearly see that the normal organization of the cells are got disrupted here due to the antimicrobial action. The same thing happens here also. This is a transmission electron microscopic analysis where we can see that these are controlled organisms where spherical organisms are there. And here, after the treatment with the silver nanoparticles, we can see that the changes in morphology of the organism, the intact organism here is got converted into fragments, and we can see the different fragments of the spherical organism here, and that clearly provide evidence on the antimicrobial action of the synthesized nanomaterials. And this is another example with another organism. And also here, these nanomaterials were also found to degrade the genomic DNA of microorganism, that also provide an indication on its interaction with the DNA of microorganisms. And this is antibiofilm activity. And stage of study, what we did is that we just used these materials to develop the so-called electrospin scaffold using silver nanoparticle by using the polymer PCl. And various analyses have been carried out on the same. And this is the electrospin scaffold membrane with the silver nanoparticles. And this is with the different concentration. You can see the silver nanoparticles in the electron spin scaffold form, coated form also is having the antimicrobial activity. And coming to the next part is with respect to the use of plant materials for the synthesis of silver nanoparticles. And already I mentioned about the use of microorganism for the synthesis of nanomaterials. And here we also use plant material here. Curcuma aromatica was used for the silver nanoparticle synthesis. And the most interesting thing here, what we could see is that here also we could synthesize the nanomaterials. And the most interesting result is here, because this is a control cell where you can see the spherical cells of the organism that remain as intact. And this is a cell which were treated with a silver nanoparticle, which are synthesized using microorganism. And here you can see that the cells were separated due to the fragmentation, due to the action of the nanomaterial here. But here in the case of nanomaterials which are synthesized using plant source, instead of separating the cells into different fragments, we can see the so-called pit formation were more prominent in this in this case. So even though silver nanoparticles are used in both the cases, but their mode of action was found to be different. And this is how it is very important to explore more biological sources for the synthesis of nanomaterials, because irrespective of the nanomaterial, this biological source which can be used for its fabrication can also play an important role in its mode of action. So that there lies the importance of exploring more biological source in the form of microorganisms or plants or plant extracts for the synthesis of this type of nanomaterials for diverse applications. And next part is work on use of biofabricated silver nanoparticles incorporated PMMA as a dental adhesive material with the antibiofilm activity of Streptococcus mutans. So this type of clinical condition with is caused by Streptococcus mutans is another important issue. And what we carried out here is we could get the pure culture of Streptococcus mutans, and these Streptococcus mutants were treated with various concentration of silver nanoparticles, and we could see the lysis of the organism in those cases where these were treated with silver nanoparticles. And so this is again, the silver nanoparticle can be an effective component which can be incorporated into already available materials and thereby to improve and enhance its efficiency and efficacy for various applications. And the creation of antimicrobial surface is again important, as I already mentioned, that various types of catheters and medical devices are used widely for various purposes, but the possibility for the commensal organism is there to get attached on the surface of this type of catheters. So what we used here is that we just used selected some of the catheters and coated with some of the nano formulations to see whether the coating of nanomaterials over the surface of these catheters, whether it will have some beneficial effect. So here, what we used is nanocurcumin was used. Nanocurcumin was coated on the catheter, and this was treated with the different organisms to see where it's like importance or antimicrobial activity. And this is antimicrobial activity of nanocurcumin. So this is antimicrobial activity of nanocurcumin against those pathogens which cause infection or medical device related infection. And this is how the antimicrobial activity. And you can see here that this lysing the organism or killing the organism. So this is an nanocurcumin treated at different stages. You can see the formation of it and lysis of the organism. This is a control cell, and like that, this was further. You can see that this is PVC tube surface or catheter which is coated with nanocurcumin and treated with organism. This is a control one. You can see that in the control there will be large number of organisms are present, but in this case of nanocurcumin coated surface, you cannot see the presence of microorganisms. So the surface coating of medical devices or catheters are very important and promising approach for providing antimicrobial surface and thereby to minimize attachment of organisms which otherwise can result in so-called device-related infection. This is in another study that we carried out with respect to zinc oxide nanoparticles in association with the curcumin. So here, a formulation was prepared by mixing zinc oxide nanoparticle with the curcumin, and this was then applied on the surface of collagen that you can see. This is a nano formulation, and this was applied on the surface of collagen, which is a wound dressing material which is widely used. And we could see that this collagen coated the nano formulation containing zinc oxide and curcumin is found to provide effective antimicrobial action. So this is the one providing insight into how these type of nano based modifications can be done and how this can be used for various applications. And this is another application of a clay nanoparticle, including antimicrobial, antibiofilm, and microbial barrier properties of PCl closely 30 within film. You can see the antimicrobial activity here, and also here the intact organism you can see, and where when it is treated with this particular nano formulation containing the clay, the organisms were found to be very less in number, and also we can see these organisms were found not to be in a viable stage. And coming to another important and a very simple method for nano material synthesis is as I mentioned, we can use various sources for the synthesis of nanomaterials. And when we think about the green synthesis method, it is very important for identifying some of the simple methods for its synthesis. And here what we use is a very simple method And here the silver nanoparticles were synthesized using the what we call as a rice water or boiled rice water. So just we took the boiled rice water and mixed it with the silver nitrate and kept it under sunlight for some 5 minutes or 10 minutes, and we could see the rapid formation of zinc oxide silver nanoparticles here. And these were further developed into so-called thin films, and these were used for another application called a food packaging application. That is another important area where the presence of antimicrobial surface is required. And here, these thin films were prepared and they were evaluated for its activity, characterized, and this is final application where we packed these materials with so-called chicken meat or flesh, and we could see that the packed materials were found to have less microbial load. So especially the meat and other materials are highly perishable in nature. So the packaging material used for its protection or shelf life improvement should have active surface or antimicrobial surface. If so, its shelf life can be enhanced, and also there will also always be concerned with the pathogens, especially foodborne pathogens, which can get introduced into these meat products. And by providing this type of nanomaterials having antimicrobial surface or antimicrobial active surface, we can reduce such concerns. So due to the lack of time, I think I am completing the mentioned time, and now I am coming to my final slide on our lab, and I just wanted to introduce our teams who are working here. And yeah, this is our team, and Dr. Sudeep is already there, and now in this Dr. Sudeep is participating offline there, and along with we have a large number of team members who are working in various aspects of nanoscience and microbiology and interdisciplinary areas. And this is our overall contributions what we could do during the last few years. And you are all those who are interested for any of the collaboration or interactions are welcome. And if for immediate contact, Dr. Sudeep is there, you can get connected to him, and or now it's open for questions. And also I take this opportunity to acknowledge various funding agencies for providing financial support in terms of various schemes, and thank you all for providing this opportunity.
It's time to ask questions. If you have any, you can ask them.
Hello, Professor Nixon. Hello. Hello. Hello.
Hello.
Yes. Good afternoon.
Yeah.
Hello, Nixon. The organ-centered drug transport using what we call the materials exhibited here is really approved by the WHO. Hello, are you audible?
I could not hear it properly. Could you please repeat?
Sir, you just don't you can disturb directly at the laptop in case of you stand here. Is it possible? Yeah, you just stand here.
Hello.
Hello.
Now audible?
Yes, please.
Organ-centered drug transport using your nanomaterial, what you have called for antimicrobial activities and so on, is approved by the WHO?
No, that part animal study we have to proceed as next stage of our study, and this is first stage of our study that we could complete. And next stage is with respect to animal study, and we have to see the toxicity concern is always there. and that we have to ensure to further proceed.
Can you able to see with the animal study experiments at this 1 or 2 slide here?
No, so far we didn't do any animal animal-based study, but we initiated some cell culture studies only.
Okay, sorry.
Dear delegates and participants, thereby we are reaching the conclusion of ICAMS 2025. We are taking a short break right now before proceeding to the valedictory function. May you enjoy a short break. We shall gather back soon. Thank you. With you all. He has done his PhD in radiation chemical studies of some Assam analogues of nucleic acid components from the Faculty of Science, Mahatma Gandhi University in 2006. Dr. Pramod G is a person who has experience in the jurisdiction of Calicut University, Kannur and Mahatma Gandhi University, as well as Kerala University. And his key functional areas include his experience and expertise in his service as research guide of the Faculty of Science, Mahatma Gandhi. Sorry, let me continue. Principal investigator of 2 major research projects funded by both DSE and UGC. He has also guided many students towards the achievement of PhD and other research projects. May I welcome Dr. Pramod for his presentation. So please.
Good afternoon to all. Thank you for the brief introduction. Being a teacher, I would like to chat with you because without students, there is no teacher. Thank you very much for your patient hearing, even in the last but not least. Environmental, sustainable and green materials. So you can hear a lot more regarding these vulnerable subjects. Of course, it is vulnerable subject because during 2024, end of 2024, as you know, in all journals and all daily publications, you can find a duration of fortnight between November 11 to November 22 in the capital of Azerbaijan. The discussion regarding the carbon mitigation and all. What does it mean, carbon mitigation? Carbon mitigation is something okay. And what does it mean? The greenhouse effect, the problem of pollution, whether it is anthropogenic, whether it is animal-made or plant-made, it is of course a question of debatable interest. Since it is our organization of St. Dominic College, Canterbury is organizing more towards the material, shall I open my discussion leads to these, what are green materials? So green materials are very familiar to you, like recycled things, biological things, and you have to prepare something synthetically like that, which shouldn't harmful to us, which does not ensure that it should not harmful to Earth's crust, it should not harmful to the atmosphere, because then only you can say it is green materials. We are the people abuse the Earth's crust, atmosphere, because we are chemists, including your Dr. Rani. We people are abusing it because we are chemists. I am very sorry to say. So look at the key type of green materials. You can find biodegradable materials like PLA, that is polyacetic acid. Polyacetic acid is a typical substance that we can make from the natural resources, but incorporating or intercalating this to some of to make it into biodegradable and user-friendly material. Look at this chart, how it is degradable, a simple chart. That's what is not working. This is the simple structural representation of PLA. That one, okay, you can find, you can synthesize it, certain stuff. You can make it be, you need to think how it is degraded, whether it is biological degradation or some other degradation, etc. Anyway, at last we can conclude that it may not harm your system. Look this simple chart. You can find, if it is green material, the end product should be none other than carbon dioxide and water. Then you can say that it is green material. My allowed time is only 8 minutes, that's why I take fast. Green composites. You have to hear a lot more about under the general title of polymer composite, etc. Green composite has some other difference than the polymer composites. What are the environmental benefits you can look in this slide? Carbon footprint is sometimes a new term for all of you. Carbon footprint is nothing connected with food. Look, nothing connected with food. You can look inside something pollution because of fossil fuel.
using the car and other vehicles. Of course, we are in third position all over the world. First is China, second is USA, and third, we are the third country generating maximum vehicular pollutants and other carbon emission materials, including chlorofluorocarbon and nitrogenous substance, etc. What we call free radicals. One Cl minus will kill 1 lakh molecules of ozone. Then you think the effect of greenhouse effect. Look, biotic and abiotic, all are very familiar to you, but you have to follow in accordance with the formula and rhythm of nature. We people are violating nature. No animal, no plant kingdom can violate atmosphere. We people are, that is why it is called anthropogenic, like that. Application across industries, you can look. In the construction field, you are always hearing concrete, but bio-related concrete is there. So in manufacturing field, in industrial field, packing of materials and other sectors you can find. So industry advantages in terms of green materials. Whether it is cost effective or not. If it is cost effective, then only the market will accept our formula. Challenges and opportunities. So we have to focus everybody for some action, and action should be constructive. Then only you have to preserve for the future generation, preserve for the nature, preserve for the earth crust. Then only our mission, vision, and look towards the future. Then we have to at least 60% fulfillment of the dream proposed by our past President Abdul Kalam. Dream for the future. If you are youngsters ready for dream for the future, you should be environmentalist. You should never be abuse the nature. Then only we can live for the benefit of future. So, shall we coming back to the nature formula? Shall we coming back to the we are ready for looking towards the future. Earth crust is not only for men but also for plant and animal kingdom. So shall we be able to promise? Shall we be able to apologize what we had in the recent past? Then only we will at least justify something to the Jesus Christ words. He is right from the very beginning of his birth till end, sacrificed for the benefit of this society, benefit of the downtrodden. But shall we be able to justify him? No, not at all. I am sorry to say, thank you very much for your patient hearing. This is our reference and reference, etc. Okay. Thank you. Say anything, please welcome. Preference will be given to the students, from botany students, chemistry students. Then only I look towards Dr. Rani and other faculty members. Come, ask some questions. This conference is exclusively for as an opening for you. Then only ask questions. Shall I take 1 or 2 minutes? 1 minute? Please, faculty members can also ask. Pardon? Oh, thank you. Water and carbon dioxide. I am ready to say a lot more and I am ready to exhibit in front of you, but my allotted time lost is only 8 minutes. That is why, how can I? Otherwise I can see you or I can send your personal email, lot more things, inventions. But time is limited. I am sorry. I am sorry. For example, in the case of in biological medicine, using bamboo, you can use, and this polylactic acid, you can intercalate, you can use it well, and the end product will none other than carbon dioxide and water. There are a lot more materials, cellulose. And I am ready to see how it is decomposed, the parameters and all, whether it is dependent on pH and temperature, some other things. I am ready, but the matter is only 8 minutes. How can I? I am sorry. Okay? Anybody? You are asking questions? Okay, thank you very much. St. Dominic College is very nice, and I have been experienced till 2015 here, interacted with the smart boys and girls of MSc Chemistry as me as a physical chemistry examiner. Thank you very much.
Good evening everyone. We have reached the concluding section of ICAMS 2025. Now it's time for valediction. As we are winding up the conference, we are here with a sense of gratitude and pride to have got an opportunity to organize and coordinate ICAMS 2025 collaboratively by the Departments of Chemistry, Physics and Botany of St. Dominic's College, Kanirapalli as part of the Diamond Jubilee celebrations. We, the ICAMS family, believe that everyone here enjoyed and gained new insights and ideas from these 2 days. Without further ado, we can start our meeting with prayer. Thank you, sister. Next, I invite Miss Anita Zoe for the welcome speech.
Distinguished guests, eminent researchers, esteemed colleagues, and dear participants. Good evening to all of you. It is with a heart weighted with gratitude and great joy that I stand here to deliver this welcome address as we have gathered to conclude the 2-day International Conference on Advances in Material Science, ICAMS 2025. We are more than proud to proclaim that ICAMS 25 marks a new era in the journey of St. Dominic's College, Kanirapalli. As with that, we step into the realms of productive research, development and knowledge generation rather than stumbling on the conventional concepts of knowledge propagation. Though we faced with unprecedented challenges, as in case of every aspect of life, we believe the purpose of the conference was met in every sense and essence. Because of the hybrid mode of operation we adopted to facilitate more participation for research scholars in and around the country, slight changes to the schedule have occurred. We are well aware that the academic community here are people of substance who can foresee such technical and functional challenges in the conduct of an event like this. However, as is expected of true academia of essence, these challenges will empower us to conduct meticulous events in the future too. Over the past 2 days, we have journeyed through the cutting-edge research in material sciences, exploring breakthroughs that redefine the boundaries and chart new paths for innovation. Allow me, dear participants, at the very outset to extend my heartfelt gratitude to our dignitaries who made this event a confluence of depth of research, clarity of vision, and the passion of discovery. May I enter into the duty entrusted upon me now. May I welcome you all to the official conclusion, the valedictory function of ICAMS 2025. First and foremost, let me extend a warm welcome to our principal, Dr. Seema Thomas, who has been instrumental in bringing this conference alive. Welcome, sir. Next, may I please welcome our chief guest, Dr. Raman Singh, who have delivered an insightful talk today and also have been with us throughout the day. May I welcome you, sir. May I take the pleasure of welcoming IQAC Coordinator of St. Dominic's College, Kanirapalli, Dr. Anup Tom Thomas, who has been supportive throughout the execution of ICAMS 2025. Welcome, sir. In one word, may I welcome you all, the delegates, participants, students, and my dearest colleagues to this valedictory function. This conference, ICAMS 2025, has been a testament to profound impact of interdisciplinary collaboration in addressing some of the most pressing challenges of our time. May the insights shared here, ranging from advancements in nanomaterials to breakthroughs in sustainable technologies, pave the way for future innovations. Once again, extending a warm welcome to you all and wish you a memorable conclusion to this transformative conference. Thank you and welcome.
Thank you, Miss. Now I humbly invite Dr. Simon Thomas, the Honorable Principal of St. Dominic's College, for the Presidential Address.
Distinguished Scientist Dr. Raman Singh, Dr. Anup Thomas, dear researchers, other resource persons, and my dear colleagues and dear students. Hope that you all enjoyed the International Conference on Advances in Material Science. So it was a test dose for our faculty and students to organize an international conference. I am sure that there are some pitfalls in coordinating certain things. That is quite natural. I was also a coordinator of international conference that is in 2011. That is in the subject statistics. At that time, you all know, there was no hybrid mode, only offline mode. Delegates from more than 20 countries participated in that conference that is conducted in mathematical sciences. So we cannot compare that conference with this one. Anyhow, it was a humble beginning as far as this St. Thomas College is concerned. I really congratulate our young faculty members, especially Dr. Arinraj, Prashant Kumar, and all other faculty members in the Department of Chemistry, Botany, and Physics. So, similar personalities all over the world. Hope that our faculty members and students will make use them also in the future research, I take this opportunity to thank all the delegates who have come over here for this national conference. I welcome you all again in our future programs. I am very eager to hear from you about the feedback of the conference. Okay, once again, thank you.
Thank you, sir. To address the gathering, I humbly invite our chief guest, Dr. Raman Singh.
Very good afternoon to all of you. I'm indeed very happy to be here for an entirely different reason which you may find fulfilling, but you may not know why I'm saying that. And I will share with you why I'm saying that. How much time do I have? As long as I want. Okay, good, thank you. My wife never says that. Anyway, I was born in a very small village in Bihar, state of Bihar, and I used to go to paddy field and then to wheat field in the morning to drive crows and other rodents away from field. I saw electricity for the first time when I was 15-year-old, and I spoke my first sentence of English when I was 21-year-old. I could write grammatically correct English. My father was English teacher, but if I tried to speak, people will think that I'm showing off or something like that. Yeah. I had the opportunity of having some brief education in Delhi. After that, I joined Tata Institute of Fundamental Research in Bombay for my PhD, but because I came from an impoverished family, I got selected in DARC, and they said, no, leave the TRFR, go to DARC, because it was a job. They wanted certainty of income. They didn't want me to continue as a student for more years. So, and that was the biggest mistake. As a matter of fact, I was working on molecular biology, and at around the same time, Govind Khurana had won Nobel Prize on that topic. But anyway, things are not always in your control. So after my training there in DARC in Bombay, I worked in Tamil Nadu at Indira Gandhi Center for Atomic Research for about 8 years. And during that time, I did my PhD from IIT Kharagpur in Bengal. The reason I'm giving you all these details is that I had a chance to move around the entire India, Bihar to Delhi, Bihar to UP. My wife comes from UP. Bihar to UP to Delhi to Mumbai to Tamil Nadu to West Bengal. And that gave me opportunity of seeing and understanding firsthand India and Indian people. And that has helped me a lot in my career, because that gave me opportunity of meeting people at every level. And after my PhD, I went to Australia and somehow either the circumstances were favorable, or Jesus or Lord Krishna or Allah, whoever you believe, was on my side. So I did manage to do good things, to the extent that I have had dinners at least with 10 Nobel laureates, and I have written a paper with one of them just 2 months ago. As a matter of fact, Ajahn Vinu, when he organized the conference in Newcastle, I was instrumental in introducing him to one of the Nobel laureates whom I met in America. So the reason I'm mentioning this is not for showing that, okay, I've been great works, or I was born in a poor family, what a poor life I had. No. Reason is sense of satisfaction, trust me. I had chance of meeting people at every stage of life. So when I meet, whether it's a rickshaw puller or a beggar or a Nobel laureate or my vice chancellor or my students, I can connect with the people very quickly. I speak, trust me, I speak the same way as I speak to my student, I speak same way to my vice chancellor, or I speak same way to you. I treat each individual as human being. Tomorrow I may not be professor, I may retire, but I will still have to live as human being. And the reason I'm telling you all these things, and it's straight away from Bible, Christ, or Srimad Bhagavad Gita, or Quran, that aspect is common everywhere. And the reason I'm emphasizing that I was very happy when Nelson was driving me from Cochin Airport to this place. There is a place where it is a church, but that church helps all the people who are going to Sabarimala. And I found that's the India that we want, where with respect to, and having come to this region, I don't know whether I'm wrong, I don't have great data and I don't have long experience here, but from a little bit of interaction, I gathered that religious divide perhaps is much less in your region. I could see that. And you should feel proud of that, because that's what is something that this nation, humanity, needs. Stay away from people who try to instigate things one way or other, and that way you're contributing to human being. Apart from what the previous speaker was talking about, working on the environment and health and all that. Yeah. Another thing that I wanted to emphasize, because it is a gathering of students, have faith in yourself. Do not do things like, quite often I'm asked this question by youngsters in India, what should I study? And I said, what's the purpose of study? Getting jobs. I said, rest assured, you will get best jobs only on the topic which you like studying. Not because somebody is studying IT and he quickly got a job and he became something. Somebody who likes something, whether you study or not, you will get there. Someone like Bill Gates, he will drop out in school, but rest is history, because he liked. It is compassion that drives you. I'll give you my own example. If I retire today from Monash University, I will be getting 80 to 85% of my salary. 82. So I'm working for 20% of my salary on the teaching, supervising, so I don't have to do anything. I retire, I become adjunct, I have 1 or 2 PhD students. Still, I work not for money. I think me and my wife have enough money that we can live the rest of the life, and I don't have very expensive life anyway. Yeah, I like to live simple life. But I work because I like working. What I do, I like my research. I like spending time with my students more than anyone else. More than anyone else. I ask my students every week. I right now have 15 PhD students. I ask each one of them, what did you expect from me? And I have not given. Only when I do that, I can ask them what I expected from them, and they have to deliver. Right? It has to be two-way traffic. So I think if one thing you could learn from this conference is to establish in your mind first what you want to do, and whether this is what you want to do, not because your parents want, not because your peers, not because in society you will be looked down upon. Don't worry about it. Do what you do. Earlier, when I grew up in an age where if you are not engineer or doctor or in Bombay side, if you are not doing commerce, you are useless. So people working in arts or something, because they could not get engineering and medical, that's why they are doing. No, you do things which you like. And if you do only that thing which you like, constructive things, not to going and being hooligan or something, doing constructive thing that you like, do that. And do with passion. Do with a passion that it does not leave you in peace if you don't do it. You ask yourself, if you do that, you will succeed. Each one of you will succeed. I tell you, people in Western world succeed not because they are more intelligent than us. We are more intelligent, I tell you. But they succeed because they do what they want to do. They are very clear about, or most of them, yeah. So that's what if you could do, you will be contributing to yourself and you will be contributing to society. Look, I don't want to speak for too long. I hope that this place grows well. I was not sure whether I should come or not, but I'm very happy that I came here, not because I gave plenary talk or anything, because I was able to meet you people. You're very warm people, you're very nice people, and make sure that you use your nice nature and self for contributing towards society. Yeah, it is straightway from Bible, from Christ, from Srimad Bhagavad Gita, that pleasure from giving. That's what our Prof was talking about. Pleasure from giving, right? Develop that, and you will get far pleasure in comparison with what you get from worldly things. I shouldn't speak, but I'm telling you from experience. All the best, and I wish each one of you great life, great success. Thanks a lot to Principal Thomas, Dr. Thomas. Thanks a lot to Dr. Arun Raj, the convener of this conference, and his team. I don't remember everybody's name. Nelson or Prashant Kumar. Sorry, I forget your name. Yeah, all of you. See, there's a problem with gray hair. You forget things very quickly. And Dr. Anup Thomas. Each one of you deserve a big clap. You have done well, but you should continue to do well. And you have basic element to do well. Trust me, I'm telling you, basic element of being good human being that I could see in each one of you. The affection that you give, that is your biggest strength. Thank you very much.
Thank you, sir. Next, I invite Dr. Anup Thomas, IQAC Coordinator, for the felicitation.
Good afternoon, everyone. Esteemed resource person of the day, Professor Clemency, sir. Our beloved Principal, Dr. Seaman Thomas. Esteemed dignitaries of the dais and resource persons, delegates and teachers from various institutions, my dear colleagues, students. The twin responsibility of a higher education institution is knowledge creation and knowledge dissemination. What happens in classroom is knowledge dissemination, and what happens in programs like international conferences is knowledge creation. I am very happy, the accuracy of St. Dominic's College is very happy to see that 3 departments, Department of Botany, Department of Chemistry and Department of Physics has jointly organized an international conference on a contemporary issue, namely advances in material science. Dear participants and delegates, for you this is a 2-day program, but being a person closely associated with my colleagues, this is the result of the hard work and sincere effort for the past 2 months. Being the coordinator of IQAC, I take this opportunity to wholeheartedly congratulate my dear colleagues from these departments for successfully conducting this program in a meticulous manner. And to the dear participants from various institutions, I hope and pray that your time at St. Dominic's was very nice. I think that you have got enough opportunity to have valid delegations and discussions with researchers, intellectuals, resource persons from various parts of the country and abroad. And I also believe and pray that this discussion would definitely add value to your research and you are able to contribute to the society through your research. Once again, wishing each one of you the very best. Let me conclude. Thank you.
Thank you, sir. Next, we would like to hear from you, your feedback about ICAMS 2025. We request the participants to volunteer and come forward to share your brief feedback, please.
Hi, good evening once again. Dear Principal and dear Professor, just acknowledge your great event and dear IPS coordinator. It's a great time and of course a feeling of pleasure that one of your strong hand is none other Dr. Rani belongs to our School of Chemical Sciences, Mahatma Gandhi University, and some of yours are very nice because I am also one among you, having only 34 years of teaching experience and principal as in 5 government-aided colleges. Now I am a retired man. Anyway, for the last 2 days, in spite of all doesn't matter. That is quite natural. All your, especially the student participants are very dynamic and some of your sir, principal sir, assistant professors are very dynamic and enthusiastic to do everything. Next time you will become IPSC coordinator place here. I did 3 colleges NAC accreditation and one among the 3 is A grade during 10 years back, not now. That time it was very valuable. Next time you will be definitely getting A double plus. Thank you.
Thank you, sir. Now it's time for the certificate distribution. I humbly request our chief guest, Dr. Raman Singh, to distribute the certificates. First, I invite Arindam Roy. Dr. Pramod Z. Miss Jyoti Nagali. Dr. Sudeep N. Dr. M. Madhavan Pillai. Reshma Rilson RJ. L. Anita Shankar. Miss Sandhya R. Shivalilal L. Patil. Thank you, Dr. Raman Singh. Next, I invite Dr. Simon Thomas, the principal of St. Dominic's College, for distributing the certificates. Mr. Hariprasad M. Parvati P. Vidya V. M. Sandhya. Mr. John Leslie Palmer. Naveed Rahman. Winnie Jose. Dr. Danyaprabha Casey. Casey Paul. Miss Anita TV. Sudhirta S. Nair. Dr. Sajikumar A.C. Dr. Shini Manoj. Jocelyn Xavier. Miss Manjusha Rose Jose. Sinsila T. Joe. Rosanna Sebastian. Sita Lakshmi K. Lal. Dr. Priya Anjali. Muhammad Shahjin J.S. Arya Surendran. E. Gauri Priya. Dr. J. Joseph. Deena Patel. Thank you, sir. Next, I invite Dr. Anup Tom Thomas to distribute the certificates. Chitra Prashant. I thank the three of you for Thank you, everyone. The e-certificates of the conference will be distributed soon. Now, I would like to invite Dr. Rani Alfonso Jose, Head of the Chemistry Department, to summarize the conference.
Respected people on the dais, delegates, dear faculties and all the participants present here. It was a wonderful opportunity for all the faculties in Department of Chemistry, Bodily Physics to conduct such a wonderful initiative from our college, especially during the Diamond Jubilee celebration. So the faculty members who were present here as participants as well as the resource persons from all over the world was really a huge experience for St. Dominic's College, Kanjarapalli. So time is running out, so I don't want to really grab your time. But to summarize this event, I feel that for faculties like us, this was a great opportunity to work between departments and to meet really wonderful persons all over the world, and also to hear from great scientists who are contributing a lot to the world. So that will all motivate our students as well as the faculties from all the departments. So I thank you all the participants as well as the resource persons who participated, and also our principal Simon Thomas sir for helping us to make this event a beautiful one. Thank you.
Thank you, Miss. Next, I invite Dr. Jyoti Abraham to deliver the vote of thanks.
Good afternoon. Respected Principal Dr. Simon Thomas, our Chief Guest Dr. Raman Singh, Bursar Reverend Dr. Manoj Palkudi, IQAC Coordinator Dr. Anup Tom, esteemed dignitaries, colleagues and dear attendees. It is my honor and privilege to extend a heartfelt vote of thanks to everyone who contributed in making this conference a grand success. And foremost, I would like to express our deepest gratitude to our resource persons, Dr. Ayyappan Pillai Ajay Ghosh, Dr. Professor Sabu Thomas, Professor Ajay Vinu, Dr. Sumit C.H., Dr. Jia Jose, Dr. Franklin Gregory, Professor Reggie Philip, Professor Raman Singh, Professor Uman K. Varghese, and Professor Radha Krishnan for making time out of their busy schedule to grace this occasion. Your inspiring research have truly enlightened and motivated us. To our esteemed speakers, thank you for your insightful presentations and for sharing your expertise with us. Your contributions have added immense value to this event. A big thanks to our live broadcasting team headed by our dearest student Joel. I extend our gratitude to our dear lab assistants of chemistry, physics and botany department for your engagement in the event. We deeply appreciate Dr. Raman Singh for your generous support, which played a vital role in bringing this event to life. Last but not least, I would like to thank each of you, our attendees, for your active participation and for making this event truly special. Your enthusiasm and engagement are what make events this so meaningful. And a very big thanks to the organizers and the team of St. Dominic's College, Kanjarapalli, especially our dear Principal Dr. Simon Thomas and Bursar Father Manoj Palkudi, who worked tirelessly behind the scene to ensure that every aspect of this event was executed flawlessly. Your dedication and hard work have not gone unnoticed. Thank you all for being a part of this wonderful occasion. Let us carry forward the ideas and lessons we have learned today and make a positive difference in our respective fields. Wish you all a great future. Thank you.
Thank you, Miss. Thereby, we conclude the valedictory function. Once again, I thank everyone on behalf of ICAMS-2025 and St. Dominic's College, Kandrapalli. Thank you.